Oh, your phone? Yeah. Where's everyone else? Yeah, mentors can sit probably over here. It's kind of where we usually congregate. Yeah, it's where we usually cluster.
Are we down a mic?
Yeah, because we were going to use a handheld mic, but the batteries are out, and they run out so quickly that. Are you okay? This?
Maybe I'll ask Mark.
Yeah, you might have it.
Yeah, I forgot. I just saw that box and I was like, oh, I almost lost it. Like $30 a piece.
You good? Oh, about the handheld mic? Yeah, go ahead.
Just quick announcement for all the presenters. So you will have these 3 wired microphones here up at the podium. Please stand behind one of the mics when you're speaking. If you're too far from the mic, no one's going to hear you. Don't.
And if you
eat the
turn
mic.
away from the mic, no one's going to.
Yeah, if you turn away from the mic, it's not going to be that great. They're okay, but please stay in front of the mic. We are live streaming and recording this for posterity.
Yeah. But don't eat the mic like this either. You can stay a reasonable distance and it'll pick up your sound just fine. Cool, so I think that everyone is in here who is going to be in here. So welcome everyone. My name is Dr. Rita Blake. I'm the manager of education here at the California Nanosystems Institute at UCLA. So welcome to the final presentations for the 2018 year of Applications of Nanoscience. So just to give the friends and family the quick rundown of what CNSI is, because you guys may not be too familiar. So CNSI, unlike a lot of the other departments here, we're not a degree granting department, so we don't give degrees, but what we do here is we enable nanoscience research, which is research all about things on the nanoscale. So we have faculty from all different parts of the campus, physical sciences, life sciences, engineering, School of Medicine, and all the faculty congregate here to do research about nanoscience. So we've got a lot of research space that is shared by faculty doing research. We've got laboratory space downstairs that houses all of our instrumentation for making and characterizing and visualizing materials that are on the nanoscale. We also have an incubator that houses, I believe at this point, is 23 startup companies upstairs on our 6th floor. So we've got a lot of different activity here, all, again, centered around pushing out nanoscience. And we also have a very thorough education and outreach program, one of the products of which is the summer program. So there's a lot of people that work to make this summer program possible. So there's a few people that I need to thank. First of all, our instructor of record, Dr. Sarah Tolbert, who unfortunately could not be here today because she is at a conference. So hopefully she's watching on the live stream, and if you are, hi, Sarah. And also Dr. Elaine Morita, who is our program coordinator and helps the wheels go straight because, you know, we've got lots of summer programs that we do amongst all the other activities. So she is the person that really helps make sure that we are all ready to go and on task with everything, and it's a lot of work. So I have to give extra thanks to Elaine every time because she's amazing. Also, we have all of our fabulous instructors that really were the keys to making all of this activity go. So instructors, can you guys all stand, and can we all give our instructors a very nice round of applause? Dominic, Zach, Stephen, Dr. Grace Wong, Ray, Shailene, Andy, Annika, and Elaine all were very instrumental at various points in teaching the students everything that they learned about nanoscience, and you will see the work that they went into actually showing what they've done through making their own projects, which is very, very exciting. There's also some staff that I need to thank because they also help the wheels on this bus actually go forward, and without them, it would be extremely difficult to manage any of this. Jeremy, who is our events coordinator, Lucas, our AV and IT manager, Nikki, our director of communications and marketing, Kevin, our events manager, who's very nicely sitting behind us, hopefully to watch some presentations. Yeah. And Mark, our digital media producer, who is also helping us get this event live streamed. So thank you guys all. And there's so many other staff that also help make this possible, so I have to thank all the CNSI staff for all of the work they do to support our programs. So we had some goals for this program. The three kind of main ones were, first of all, to expose our students to advanced topics in nanoscience. And most people, you know, haven't even heard of the word nanoscience. I know I didn't hear about the term nanoscience until I was about halfway through my undergraduate career. So we wanted to give students a really thorough understanding as they're still in high school, to really show them about what the cutting edge of a lot of different fields of science is. I mean, most fields of science, everything is starting to kind of center around nanotechnology because it's so ubiquitous, and we've explored a lot of stuff that happens on the big scale, but the smaller scales like the nanoscale are still a little more unknown to us. So it's a very big field, so we wanted people to be exposed to it. We also wanted to give them education beyond just the typical sort of classroom education and give them skills in science literacy, science communication, and you know, the other 90% of the job of being a scientist, which isn't just about knowing a bunch of science, but also about the process of learning science and the process of communicating science, which is a key element to being a really successful scientist. So we wanted to give them a very well-rounded education. And I think we've done that pretty well. And I think maybe the one thing that we've taught them the best thing of is probably lab safety. So we have some really good lab safety footage of all of them. I think you'll be very, very proud of what they look like.
Apples. This one for me. Uh-oh. I gotta clean that. I will build it. Uh-oh, I built
hella profesh. Just kidding, of course. They did much better than that. Well, at least a little bit better than that. So what you guys are going to see today is the product of a very, very short span of time, really only 2 weeks of work. And it's really, really incredible what students are able to achieve, starting from near zero to a final product that is actually quite compelling. So we're very excited about all the projects because we've been seeing them progress all week. So I hope you guys are going to be excited too. So with that, I think we're just going to get right to it because we've got lots of presentations to go through. So first group, please come up on deck. So each group is going to have up to 10 minutes to present. Afterwards, we're going to open it up to Q&A. Audience members, we would like to ask you all to do questions first, and then instructors will come in with some extra questions. But we really want to open this up to students and parents and friends and family to ask questions. So please do feel empowered to ask questions.
Good morning, everybody. Our presentation today will be on detecting charge state in energy storage devices. My name is Rashad Menezes.
I'm Kayla Mays.
I'm Brenda Dewan.
I'm Lakshay Maharana.
And I'm Alexa Silfen.
So our main goal for this experiment was to determine if we could use color as an indicator to determine the charge state of an energy storage device, such as a battery, a capacitor, or a supercapacitor. And we'll be, over the next couple of slides, we'll be explaining specifically how we did that and what we did in our experiment to actually achieve that.
So we wanted to see how our research idea and question could fit into the application of artificial muscles. So basically, artificial muscles are made of biomaterials that are made to mimic the elasticity of normal muscles. And the way that these muscles actually move is there is some kind of battery or capacitor inside of them. And depending on the amount of applied voltage that you apply, there are different electrochemical signals that are sent that make these muscles move. So the only way, though, that you would be able to test the state of charge of this battery or capacitor would be to put a multimeter into the actual capacitor or battery. However, this is not practical because you'd actually be putting a multimeter into your skin and into your muscle, and that wouldn't be practical, like I said. So the way that we were trying to go about solving this issue was to see if there is a color indicator that can detect the state of charge of a capacitor or a battery within the muscle.
So we came up with a research question and a hypothesis for our experiment. Our research question is, can color be used to determine the charge state of a supercapacitor using an indicator? And with that, we came up with a hypothesis for our experiment. We expect the pH of the electrolyte to change as a result of the electric field changing the equilibrium point of the water ionization reaction. So what exactly does that mean? So water self-ionizes during this process, which results in an increase in the H3O plus ion, which makes it more acidic. But because it's becoming more acidic, then we have to connect this back to the electric field changing the equilibrium point. When a battery is fully charged, there's a high electric field, and when it's discharged, there's no electric field. So this is how we're going to see a connection.
Okay, so like I mentioned before, there are multiple types of energy storage devices that could be pertinent to our project, but we specifically focused on supercapacitors. So a supercapacitor consists of three main things: two electrodes, which are specifically shown in the diagram, and then in between the electrodes is the electrolyte solution. What we did is that we connected our own supercapacitor to the breadboard and then to apply voltage, and that specifically allowed for electrons to go through the supercapacitor and create electricity. We then also created a shift in the electric field, and that helped us determine if we could use color as an indicator for our project.
So in terms of the actual experiment we used to test our hypothesis, we divided it into two basic steps. The first was to build and test an actual supercapacitor, and the second was to test the pH as the supercapacitor charged and discharged to see if there was any change. To this point, our first step in making the supercapacitor was to make electrodes. We used carbon black, a mixture of micro and nanoparticles, combined with several binder solutions, including a chemical called CMC, Teflon and isopropanol to make this powdery carbon dough into a Play-Doh-like paste, which we then flattened out. The main reason for flattening this out is to allow electron diffusion to happen more easily through the electrodes.
So in order to make our carbon black dough, we had to cut dried pieces of carbon black and put them into isopropanol. And then after that, we submerged the carbon black dough into citric acid electrolyte for 5 minutes. So then after the carbon black dough had soaked, we began to assemble our supercapacitor. And here we have our stainless steel, and that acts as the electrode. And then our carbon black dough acts as a coat for the plate. And the supercapacitor is just like a sandwich, so we just put the two plates together, and then the paper towel soaked in the electrolyte, and the brown paper towel act as a separator for the two plates.
So basically, we ended up making about 5 supercapacitors, each with a different design to facilitate putting in a pH meter or different varying amounts of solution. And if you can see in the top left-hand corner, that's actually just like a frame that has a window for another capacitor we could have made. And we actually created one design that had a window in case we were using potential indicators to see the state of charge. So in order to check if the supercapacitor actually worked, we hooked up some alligator clips and put those onto a 4-stage switch and a breadboard to see what the voltage was and to check if the supercapacitor actually worked at a charge and discharge state.
So since we had enough evidence that the pH had changed through our pH meter, we decided to not continue on with our trials, and we were also feared that if we tested with the water, the circuit would corrode, and then large portions of water would affect our experiment.
So these results were actually very surprising. In electrochemistry, there's Le Chatelier's principle, which addresses a lot about how equilibrium shifts according to conditions. And electric field is actually something that's not really mentioned much at all, or at least as anything as much important. So because in our experiment, we found that it does affect it, it's definitely going to be something that will be available for more science research in the future. We also want to mention that we did a no water trial and a 5% water trial. The no water was our proof of concept that it works, and by adding water, we showed that you can change the pH range. As you can see on the one on the left, it goes from 1.97 to 1.60, and on the right, you can do 2.2 to 1.89. So because you can change it according to the amount of water, you can change the types of indicators that you're going to use, although you'll see which one we chose for our specific experiment. One more thing is that batteries are typically created in a glove box, but we did not do ours in a glove box. It's normally created in a glove box to prevent any water, but ours withstood the conditions when we created it in where we were.
So even though we did not have access to thymal blue or any particular indicators, we predict that thymal blue would be the best indicator based on our range of pH. And as you saw on the last slide, we had a very narrow pH range. And since it fits the range that thymal blue has of about 1.2 to 2.8, this would be the best possible indicator. And we would probably be able to test this in a future experiment.
In terms of future applications and further research that we could take this experiment on, the first would be to check thymal blue's sensitivity to our changes in pH. Although we know that it fits our range, we do not know how sensitive it is to a battery's unique changes in charge. Our second application would be more of an engineering application. Most batteries are sealed within a protective case. You can't really see if they're changing color. So our second application would be to actually engineer a way for the indicator to be exposed on the outside of a prosthetic and interact with the battery at the same time. Here is a picture of a fully charged, partially charged, and fully discharged battery along with thymal blue's colors according to our pH results.
Thank you for listening to our presentation. We're going to open it up to any questions if you have. Okay, the question was, can you provide a nanoscience foundation for our work?
So the primary component of our experiment that involved nanoscience was in making carbon black electrodes, and that was mainly to increase the surface area. As you might know, capacitance is directly linked with the area of the electrodes produced. So by using nanoscale materials, we were able to maximize surface area and therefore maximize capacitance.
What's your conjecture on how, when it's actually placed, how effective or how sensitive your measurement is going to be?
Okay, the question was, what's our conjecture on once it's actually placed, how sensitive will it actually be?
So while I said earlier, we do have a range for thymal blue, we are not entirely sure on how sensitive it is to changes. So as we do not have access to that material, we cannot accurately say how sensitive it would be to changes. And we would also like to say that it's very specific based on the kind of indicator you use. Would it have skin effect? The question was, would the indicator have a skin effect? Not if it was contained. That's, again, more of an engineering application and a further step for our research. However, if we were to incorporate that into a battery, the indicator would obviously be contained so that it did not come into contact with any skin.
Like Brenda showed, there's a duct tape casing that we put around, and a window, actually like a plastic slide that you could see the color through. So like Rashab said, it would be mostly contained, and you wouldn't be able to harm your muscles or anything.
Yes?
The supercapacitors you made were clearly made for a test of a concept. How much energy can you store in those when fully charged, and how does that compare to how much energy you have to have in the capacitor for the actual application of artificial muscle?
So we actually made a graph to show the works of our supercapacitor.
So so the blue line specifically looks at the charge state of the supercapacitor, and we plotted it from 0.5 volts to 2.2 volts. And you can see that specifically as you added more voltage, you had less current because more voltage meant more resistance from the electrolyte solution. So we were looking for that optimal sweet spot, which is the plateau, and it's around 1.3, 1.4 volts. Just to put it in context, to power an LED, it's around 1.7 volts.
In addition to that, what you said is perfectly true. The supercapacitor is more of a proof of concept. This application is meant to apply to not only a supercapacitor with a citric acid electrolyte, but also any form of electrochemical energy storage device.
Comments from the instructors? I thought it was great.
Thank you.
Up to the audience, too. Those were some tough questions.
Any other questions? And if not, then
No, it's not our computer.
Good job on backup.
Yes, backup slides. Oh, and thank you for repeating the questions that were asked. I forgot to make that announcement, so thank you for doing that. Very well done.
Are we going to use the clicker or are we going to press? We're going to speak.
Can everyone say? Yeah. Hold on, we'll share a microphone. Are we ready? Wait.
Hello everyone. Today we are going to be presenting our project using iron oxide nanocrystals to mimic the tactile senses of skin. I'm George.
I'm Vishal.
I'm Yo-Yo. I'm Samantha.
I'm Holden.
So why does synthetic skin matter? Why is it important to us? Well, basically, if we are able to create a synthetic skin that can sense and detect pressure, we can help return the sense of touch to amputees, including those who have fought hard for our country. It is necessary that we work hard to help these amputees respond to certain stimuli that are very important for survival, including pressure, so that they may feel once again.
But before we can create a synthetic skin, we have to understand how human skin works. Now, there are 4 types of mechanoreceptors in human skin: Merkel's discs, Mesner's corpuscles, Pacinian corpuscles, and Ruffini endings, as you can see here. These send soft touch, vibration, stretching, and high pressure, respectively. We understand that it would be impossible to mimic all of these senses in just 1 week, so we decided to focus mainly on the Ruffini endings, which detect pressure. When pressure is exerted on the skin, the Ruffini endings compress, which makes sense given their pump-like shape. And when the Ruffini ending is compressed, an electric signal is emitted through the nerves.
We believed that our synthetic skin would be receptive to pressure because when our skin is pushed closer together, the nanoparticles are able to pass current with more ease, and therefore the skin becomes more conductive.
Now that we understand how human skin works, we can discuss the synthetic skin. Now remember, the goal for our synthetic skin is to detect pressure. So on the left, we have an image of the actual synthetic skin that we created. And on the right, there's a cartoon diagram that will help us explain our synthetic skin in more detail.
So our synthetic skin has 2 parts. The first part is the PDMS, which you can see as the blue block on the screen. The PDMS is a synthetic rubber, so it is both flexible and insulating, just like human skin is. The second component is the iron oxide nanocrystals, which you can see as the black dots in the diagram. The nanocrystals are embedded into the PDMS, and together the PDMS and the nanocrystals can allow us to detect pressure with our synthetic skin.
So to make our synthetic skin, we needed something that's rubbery and stretchy like our own skin, so we decided to use a silicone rubber gel called PDMS. So when we made our PDMS, we used a base and a curing agent that react when it gets heated up, and since PDMS is really insulating, we added iron oxide nanocrystals in order to conduct electricity better.
So we've talked a lot about synthetic skin and what it's made of. Now I'm going to explain how it actually works. On the right, you can see a zoomed-in image of the synthetic skin. The black dots are the iron oxide nanocrystals, which are electrically conductive. The white background is the PDMS, which is an insulator. Current flows between the red and black terminals of the multimeter when electrons jump from black dot to black dot, or from nanocrystal to nanocrystal. Conductivity increases with pressure, which is depicted in the 2 diagrams. The left-hand diagram is a zoomed-in image of our synthetic skin when no additional pressure is applied. As you can see, the black dots, or the nanocrystals, are quite far apart. This makes it difficult for the electrons to jump from black dot to black dot, or from nanocrystal to nanocrystal. Because it's so difficult, there's only 1 or very few paths that the electrons can take between the terminals of the multimeter. So when there is no additional pressure applied to our synthetic skin, it has very high resistance and low conductivity. This is sharply contrasted in the diagram to the right, which is a zoomed-in image of our synthetic skin when there's high pressure applied. When pressure is applied on the surface of skin, the skin is actually squeezed together. So the black iron oxide nanocrystals are actually closer together. This short distance allows electrons to very easily jump between nanocrystals. So it's very easy for them to get from one terminal to the other. It's also because it's so easy for them to jump from dot to dot, the electrons can travel on multiple different paths. So when there's high pressure applied to our synthetic skin, it has a very low resistance and high conductivity.
So we wanted to test out just how well our skin could detect pressure. To do this, we measured the resistance of the synthetic skin when we squeezed it and when we released it. As you can see in the video on the right, when pressure is applied, the resistance drastically drops compared to when no pressure is applied.
This is the graph we produced from our data. Note that lower resistance corresponds to high electrical conductivity, as the electrons can move far more easily. So the 4 plateaus that are circled in red on the graph are the resistances when no pressure was applied. These are the highest points on the graph because when no pressure was applied, the nanocrystals were quite far apart, as I spoke about earlier. As you can see, the resistance always returned to nearly the same value because at each of these four intervals circled in red, no additional pressure was applied. So the green, purple, and orange highlighted sections on the graph are when pressure was actually applied. The most pressure was applied in the orange section, while the least was applied in the green section. As more and more pressure is applied, the resistance continuously decreases. Thus, the synthetic skin can differentiate between different amounts of pressure. This result is quite remarkable, as it means that our synthetic skin can not only detect pressure, but it can differentiate between varying amounts of pressure, just like human skin does.
We also tested the conductivity of our synthetic skin quantitatively by pressing a known weight onto it. In this case, we added 50 milliliters of a heavy sugar solution every minute and recorded its resistance every 2 seconds. When graphing our data points, we found that there is an exponential relationship between the resistance and the weight of the solution. We can conclude 2 things from this. One, our calibration curve allows us to calculate the weight of a surface based on the resistance that it experiences. And 2, similar to our own skin, the synthetic skin is more responsive to small pressures than large ones. For example, you could easily feel the difference between a fly and like a raspberry, but the difference between a watermelon and a poodle would be much harder to compare.
So after conducting our experiments, we were able to conclude that the mixture of iron oxide nanocrystals and PDMS can conduct electricity, and the synthetic skin model that we made can sense pressure through the changes in resistance across the suspension. In the future, we hope that the synthetic skin may be connected to the user's nerves so that the user may instantly recognize when different amounts of pressure have been exerted on their skin. Also, in the future, synthetic skin may be designed to respond to different types of stimuli, including changes in temperature and vibrations, and these would allow the user with synthetic skin to feel almost exactly how they will with real skin. And this man on the right, as well as many others, would be able to benefit tremendously from this technology. Thank you.
So the question was, did we do some preliminary research on what has already been done with synthetic skin? So we did some research on the current applications, especially in the medical field, and we found that skin grafts are used far more commonly than synthetic skin. We also looked at some research that one of our instructors, Stephen, did to see some of his results, and he found that, while he did no experiment, he found that this field would be quite promising. So based on that, we decided to do an experiment and see if we could make synthetic skin of our own.
It's very striking how much the resistance in the synthetic skin changed with pressure. Did you make any effort to try to measure how much the width of the skin compressed when you had it at these different weights or different squeezings by hand?
So the question was, did we make any effort to measure how the squeezing affected the width, correct? Well, we did not measure this quantitatively, but when we were doing the actual squeezing, we found that because the skin was quite thin, I mean, it is supposed to be like skin, there was not a measurable difference. So while it might have compressed a few millimeters, it wasn't like it went from very thick to extremely thin. It is a rubber, so it doesn't compress that much.
Did you guys make any attempt to actually measure the amount of pressure that you were applying for your systems? Because you talk about a little, like small pressure, medium pressure, I think, and large pressure. Do you know what those values are?
Why don't you talk about that, Grace?
Sure. Well, for the qualitative experiment that we did use our fingers, so it's not exact how much pressure was put on, but we also conducted an experiment that's quantitative where we measure the amount of weight that's being pressed onto the synthetic skin so that we can create a graph.
So this graph was used to make a calibration curve. So at a given resistance, we can show how much weight is being applied to any surface. And knowing the weight on the surface, we could calculate the pressure and the force being applied to the surface if we knew more about the weight distribution and the dimensions of our skin.
Could you go back to the previous slide? Because you have your resistance in microoms here, or on the sugar solution slide.
Yeah.
And this should be comparable to the resistance that you're measuring with the pressing, right?
Yes. Let me. So on the multimeter.
Yeah, the one before this.
Sorry. Here.
Yeah, because they kind of line up. I think so this is an offset, it's about like 170 megohms.
Okay. And then here.
So you created a calibration curve,
Mhm.
correct? And so then you can take that calibration curve and calculate out the amount of pressure you put on in terms of weight based on the calibration curve that you created.
So, can you repeat the question?
So basically, 17 it's a fairly small amount of mass.
So, as you pointed out, they are different, but I believe this was a different sample from a new batch of skin that we made because we made the skins in the 2 batches for 2 different experiments. So, because we could not control exactly how many nanocrystals were in it and in what proportions, it makes sense that the results are not don't match up completely.
I was just saying that you could have used this graph to calculate the pressure when you're squeezing it, because this is a calibration curve.
Yeah.
Right.
This is relative only to one sample, and then the other graph, the squeezing, was relative only to that sample.
Any other questions? Okay. Thank you.
So hello everyone. My group members and I did our project on conductive ferrofluids to make reconfigurable liquid circuits for computing applications. My name is Apurva Chanda.
I'm Megan Stalick.
I'm Eileen Rashid Faroki.
I'm Ethan Wong.
And I'm Josh Rong.
All right, so you may be asking, why are liquid circuits better than solid circuits? And the answer to this is solid circuits are embedded in silicon chips, and this means that whenever this technology comes out, you're pretty much limited by it. You can't change it in any way. So the benefit of a liquid circuit is that you can reconfigure it to optimize it to the best technology that we have to date. And pretty much all you have to do is download a schematic and then apply it to your circuit so that it can create different pathways and different combinations that would be favorable.
So we first asked the question, what can we use to make our liquid circuits? And this question was actually fairly easy to answer, considering that ferrofluid is the only liquid that is easily manipulable, like easily controllable. And then this is because it is a combination of conductive magnetic nanoparticles with the properties of a liquid. So when you apply a magnet, it easily follows the magnet, but when there's no magnet applied, it acts like any other liquid. And fun fact, it was first used by NASA to move fuel in space.
So our main research question was, how do we make these ferrofluids conductive enough so we can use them in computers? And we hypothesized that a salt solution would be the best for this because it would produce enough ions for our ferrofluid to be conductive enough. And so the main impact and significance of our research was that it would create long-lasting technology. We wouldn't have to keep rebuying our computers, TVs, and phones, and instead we could just update as long as new technology was invented. And actually, ferrofluids have been used in computers before. They're used in hard drives to protect rotating elements in computers from being contaminated by dust and dirt. So we decided to take this a step further and use ferrofluids in other parts of a computer.
So here we have a diagram of the model that we made to test this liquid circuit. And right there would be the ferrofluid, and it's connecting this one circuit right now, turning on the red LED. And it can be manipulated and moved to different circuits and turn on the different lights, representing the different bits of the computer. And we do this with a magnet on the bottom, and we can use it to drag the ferrofluid to wherever we want on the slide, completing the different circuits.
All right, so we designed our experiment in the following way. So we, as Josh said, we constructed our circuit in the way with 3 LEDs connected to a battery with switches in the that sort of interrupt that circuit, and then these switches can only be turned on when the ferrofluid makes contact with both copper contacts, and then whenever the ferrofluid completes that circuit, we should see individual LEDs turn on. So in order to understand how these the ferrofluid works, we kind of have to understand how we synthesized it. So we used iron chloride solutions and a base called ammonium hydroxide, and when we mixed it, we created iron oxide nanoparticles and a byproduct called ammonium chloride. So in this video, we can see how we synthesize this. Whoops. Okay, so as you can see, in the brown liquid is the iron chloride, and then what we're pouring in is our base, ammonium hydroxide. And as we're pouring it in and swirling it around, you can see that the color of the solution kind of changes, and this indicates that we're creating a new compound, which is our iron oxide nanocrystals. And as you can see, it's kind of black, like the images we saw earlier of the constructed ferrofluid.
There was one specific reason why we decided to go with the ferrofluid. This is because this fluid is easily manipulated. When it's surrounded by a magnetic field, it can be controlled and it does what we want it to do, but without it, it acts like any normal liquid. So we decided that this would be an easy thing to control and a best choice for us.
So as you can see in the video, as the ferrofluid is put on the plate, and there is a magnet under the plastic that is moving the ferrofluid, and as it moves, the LED lights are turning on. However, the ferrofluid was not as electrically conductive as we had expected. That's why the lights are fairly dim, but the ferrofluid is very easily movable to control, and it's fairly reconfigurable. So because the ferrofluid wasn't as electrically conductive as we had expected, we added salt to it, which caused the LED lights to be much brighter. However, it was harder to control the ferrofluid, and since there was salt in the ferrofluid, it stuck to the plate a little.
Looking at the side-by-side view, you can clearly see the difference between the brightness in the LED bulbs. Specifically, if you look at the green bulbs, the top solution is the one without salt in it. It is less conductive, but is easily workable. As you can see, only one LED is on in that picture, as opposed to the second picture with salt. The bulbs are brighter, but all 3 bulbs are on, as we were unable to move the ferrofluid as easily as the one without salt. So this relates to a computer chip, because it's kind of a proof of concept that we can manipulate which LEDs, or like which bits we turn on. And when it's off, it represents a 0. And when it's on, it represents a 1, like your binary in your computer. This is kind of like a proof of concept, because if we can switch between these 3 LEDs, we can, in theory, switch between as many ons and offs as we would need to.
All right, so in conclusion, this demonstrated that we can use a conductive magnetic liquid. In this case, we used a ferrofluid, and we used it to construct a reconfigurable liquid circuit. So if this were a solid chip, it'd be impossible to reconfigure the connections without a mechanical switch. So this is a new area of research that can produce some promising results in the future. We just need to sort of fine-tune it and sort of get a bit better at controlling our magnetic fields.
So some possible future applications is that we could have a liquid computer chip, as long as we are able to manipulate the ferrofluid precisely and control the magnetic fields. Additionally, today our software is updated multiple times a year, but our hardware is not as of now. And if we use this system, our hardware can be updated as frequently as our software.
Any questions? Yes.
The processing chip doesn't just have a switch to do on off. It has transistors, diodes, and all those things. How do you think you can make those kinds of components using ferrofluids?
It's still a pretty new. Oh, okay. So the question was, right now, computer chips use transistors and diodes, not just turning on a switch. So this is a pretty new area of research, and we think that as we go deeper into this area of research, we can figure out new ways to simulate, or not simulate, to replace what we're using right now as physical chips. But as of right now, we're not really sure how that would work.
One thing that's very striking about your video is how much more viscous the ferrofluid looks after you've added salt. At this point, would you speculate if you had unlimited time, would it be different concentrations of the salt or different compound to make it conductive that you would try next?
So the question was about the concentration of the salt and how it made the solution much more viscous. And yes, if we had more time, we would play with other ionic solutions to not make it as viscous but still more conductive. We were looking at like citric acid, but unfortunately we ran out of time. We're unable to try those.
To add on to that, we did use lower concentrations of our salt water, our ionic solution, but when we mixed it with more water, it sort of made our iron nanocrystals fall out of the solution, so it wasn't suspended in the solution anymore, and it was all the nanoparticles were sedimented at the bottom with all the liquid at the top. So yeah, in the future, we would like to explore different ionic solutions. Yeah.
So a lot of your work in trying to help control the ferrofluid moving along the surface better was focused on editing the flow mechanics of the fluid itself. Did you think at all about maybe a way that you could manipulate the surface so that it moves better between the different switch states?
Yeah, so we were, at first we were planning on using a hydrophobic and hydrophilic surface in order to create pathways for our ferrofluid to follow. But the problem with this is that we were trying to use we were going to coat it with DCT and MUO, which are respectively hydrophobic and hydrophilic surfaces. But those only bind to metal, and we didn't have the materials necessary to do that. But we also changed our glass slide at first to an acrylic slide because our original ferrofluid it stayed on the surface instead of spreading out and staying where instead of staying where it was when we were moving the magnet. Yeah.
You mentioned that the nanoparticles were crashing out when you had low concentration of salt.
Yeah.
Why was it crashing out?
Well, we first mixed it with salt water, and we're not exactly sure why it crashed out. Except we have some theories. Maybe the coating on the iron nanocrystals, which was a polar compound called TMAH. Maybe that wasn't strong enough to withstand, some of the different forces within the ionic solution.
Students, any questions from you guys?
Thank you.
Some good questions for the next one.
Thank you.
Thank you.
Thank you. All right, next group. Team 4.
Is Team 4 here? Okay.
All right, this week we've been testing effects of temperature and UV on superhydrophobic and superhydrophilic nanostructures. My name's Katie.
I'm Jaden.
I'm Ryan.
I'm Amisha.
I'm Jonathan.
And we're
Team 1.
Okay, so you may have noticed the words superhydrophobic and superhydrophilic on the slide before. These concepts are the core of our experiment. But what do those exactly mean? Let's break it down. Superhydrophobic. They include the word phobic, referring to its characteristic of repelling liquids, especially water and other polar liquids. The coating of superhydrophobic surfaces is usually nonpolar, therefore repelling, as you can see in the lotus leaf and the self-cleaning surface on the shoe. Superhydrophilic surfaces, on the other hand, attract water. As you can see in the diagram on the bottom, the water on the surface is attracting and it's spreading out.
So contact angle is usually how we measure how hydrophilic or hydrophobic something is. The higher the contact angle, the more hydrophobic something is. So what we do is we put a drop of water and then we use a machine called a tensiometer to measure the contact angle. So for our experiment, as nanoscience research is getting more and more prevalent and the applications are becoming more and more clear, we wanted to see how extremes of heat would affect these surfaces that we made, the superhydrophobic and superhydrophilic surfaces. So we used very high heats and very low freezing points to see what would happen.
Now, this directly ties into a very, very important field for all of the products that we use nowadays, which is reliability testing, which is essentially to simulate long-term use. You put any item through extreme conditions. You know, take example for a car, you would run it at like 200 miles per hour for an hour to simulate a couple months of driving. So this is really important for many different chemicals and how we use them in our applications because a lot of things that we use nowadays, especially in terms of industrial manufacturing, need to withstand long temperatures or interchanging temperatures for long periods of time. That's where our experiment comes in. Future research could develop more, in industrial applications, something that's hydrophobic that can withstand super long exposure to very high heat, or in some cases intervals of very hot or very cold exposures. And another application of this is also in airplane defrosting, where when planes fly, they're in high elevation, they have to deal with very, very cold temperatures. And so a big problem is ice forming on the wings. If you have something that can withstand that cold temperature and also retains its hydrophobic capabilities, then you now have that problem solved.
So another core concept in our experiment is nanocrystals. We began with a piece of unsanded copper. From the naked eye, it's just a piece of copper. But when we go down to the nanoscale, after sanding, we can see that small ridges form. These ridges increase the surface area, which is very important for our experiment. We then put this sanded copper into a solution of silver nitrate. The silver nitrate forms the nanocrystals, which thereby increase the surface area even more.
So after we put the silver nitrate on it, we either coat it with MeO or DCT, also known as
11 mercapto, 1 undecanol, and 1 decanothiol.
And the MeO makes it hydrophilic. As you can tell, the water is closer to the surface. And the DCT makes it hydrophobic, and it repels the water and makes it like a ball. So our question is, will heating and cooling affect the hydrophobic and hydrophilic properties of the nanocrystal and non-nanocrystal surfaces?
So we think that setting our samples of super hydrophobic / philic samples, they will probably degrade at extreme heat because all the molecules are like moving really fast and they're more prone to change. While freezing it probably won't do anything because all of them are just frozen and like not moving much.
So for our experiment, we had a total of 45 samples, which we divided into 3 groups, 15 each. The first sample group had just plain copper, unsanded. The second group had sanded copper coated with silver nitrate and DCT, a hydrophobic surface. And the third group had sanded copper with silver nitrate and MuO, making it a hydrophilic surface. We then exposed these samples to extremely hot and cold temperatures, ranging from 200 degrees Celsius in an oven to negative 271 degrees Celsius using liquid nitrogen. We also exposed some to room temperature to keep them as our control. We then measured the change in structure by comparing the previous and after contact angles.
So before we begin our experiment, it was important to note that copper in room temperature forms copper oxide, So then we had to scrape it off to bind it to the silver nitrate, which we can coat with MU and DCT. So to create our samples, we have 45 pieces of copper. We sanded 30 of them, or 2/3, and then we coated them in silver nitrate and DCT to make them super hydrophobic and super hydrophilic, respectively. We then measured the contact angle to see what it would be at room temperature, and then we then exposed the samples to the extreme temperatures of 200 degrees Celsius and 80 degrees Celsius and negative 271 degrees Celsius to see the freezing and heating would do to them. And then we re-measured the contact angle to compare the differences.
So we had a certain amount of expected results. As we said earlier in the hypothesis, we expected the samples exposed to extreme heat to degrade and lose their properties, whether that be super hydrophobic or super hydrophilic. With cold, we expected little change, because the cold would essentially decrease the energy moving around in the samples and stop them from degrading. And with the control, we expected no change because that's the point of a control. We didn't change as many variables. One important aspect of why we expected the heat to change is not only does the heat degrade the molecules, but the heat would actually cause the copper to expand using the thermal expansion equation. However, it's important to note that this would be on a very micro scale. It only changes by a couple nanometers. But on the nanoscale and in the nanoscale structure of the silver nitrate crystals, that could have a different impact.
So for our copper plate results, we can see that the temperatures at negative 271 degrees Celsius, negative 20 at room temperature, and at 80 degrees Celsius were all about normal. But at 200 degrees Celsius, the copper actually had a much lower contact angle, meaning it would be a lot more hydrophilic. For our DCT, which is our hydrophobic results, we found that although the ones at the different temperatures had a slightly different change, the one that we expected to change at 200 degrees Celsius did change a lot, and it also became a lot more hydrophilic. For our MUO, our super hydrophilic surfaces, we found that they're almost all the same, except the outlier that our room temperature, it actually became a lot more hydrophobic and increased 34 degrees, and at 200 degrees Celsius, it did increase 50 degrees.
So let's stop for a second. What could have caused that increase in room temperature? Our MUO contact angle changed at room temperature by 34 degrees. This could make the difference between a hydrophilic surface and a hydrophobic surface, which it did. So we decided to look into the potential causes of this change leading into our second trial. So our causes, which we thought of, were atmosphere. Perhaps there were some gases in the air that could have reacted with the copper. And then there also could have been a potential of sunlight and UV radiation causing changes in the surface, which is what we tested next.
So when we tested sunlight, we saw that MUO had the greatest difference, meaning it could explain why the room temperature changed so much. And when we tested UV, we had the same result. It became more hydrophobic by 33 degrees.
So in conclusion, for our MUO, especially as we saw by the UV light, there was a drastic change between the room temperature as compared to the other tests. For the DCT, it was as expected. The DCT began to burn off at the extremely high 200 degrees Celsius temperature, but other than that, there were not many large changes. The copper plates, now this was very different from what we expected. The contact angle actually started to decrease as temperature went up, which could potentially have some future testing. And as we also saw, the sunlight and the UV light also caused an MUO change. So in conclusion, MUO is affected by sunlight while DCT and normal copper is not.
So this leads us to some future testing we could potentially do. First of all, we could potentially test the copper with and without the oxidized layer on. And then we could also test a lot more different temps, like higher than 200 or lower than, okay, not lower, but or just around the same as the one we tested. And then we could also test this with a lot of different metals that wouldn't just degrade at 200 degrees Celsius like our control did.
Thank you for listening. Are there any questions?
So the question was why we chose copper. The reason why we chose copper is because it would bind to the silver because we don't have a lot of money to spend on silver, so we can't just use silver nitrate and bind it with DCT and MUO. We could just scrape the copper off and it would bind to the silver nitrate.
In addition, it's also an example of how nanocrystals and nanostructures help increase the surface area and therefore affect the superhydrophobic or superhydrophilic properties. So it pertains more to nanoscience than if we just use copper and then soaked into DCT. I mean, silver and soaked into DCT, because that's where the bond forms.
How long did you expose the surfaces to extreme heat or ultraviolet light? And what implications do you draw from your testing to how these might be affected in actual commercial and industrial applications?
The times varied somewhat, not a whole lot. Looking specifically at the super high heat, we were talking with a lot of our instructors about the implications of putting it for a long amount of time versus a short amount of time. Initially, as you saw, we had 80 degrees Celsius as our max, but as we saw, there was essentially little to no change, and so we thought, why not go to the extremes or as high as we can and safely. So we put in, the samples we put in for 200 degrees Celsius, we put in at the oven, 200 degrees, for 1 hour. And initially we were going to do 2 hours, but limited by time because we didn't have as much time, and also by the realization and talking with our instructors over here, especially Steven, shout out. He said that if it wouldn't be damaged for at 200 degrees Celsius in 10 minutes, it wouldn't really change that much for 2 hours. But we wanted to keep some consistency because the 80 degrees samples we had in for 2 hours, so we wanted to at least have it for a long time from. So that's why we kept it in for only 1 hour, and we did see a very significant change. Oh, and someone else want to cover the future implications?
Oh, yeah. So what we want to see was basically that we wanted to replicate how a long period of time at a relatively normal temperature, but we couldn't exactly do that due to time limitations, so we did an extremely high temperature in a very short amount of time. In the future, perhaps when we do have more time, we could try it with larger amounts of time at a normal temperature to see if it replicates the results that we found earlier.
In addition, another thing we were thinking of doing that we couldn't do according to time constraints is intervals between high heat and low heat, because that change could potentially degrade things a lot more than just being exposed to one temperature consistently. Stephen?
The UV, you said sunlight degrades the MUO. Was it the UV or the sunlight? Both.
Yeah.
Okay, dang. So I was hoping it would be one or the other so we could figure out what was causing it. And then my second question, which I honestly have no idea to this answer, so it might be tough, fair warning. MUO and DCT have the same sulfur bond. The only difference is 7 or 8 carbons later, there is an OH molecule. How is that allowing UV light to degrade MUO, but not DCT?
We don't know, but we have a couple guesses. Of course, this is relatively uneducated because, I mean, we've all taken chemistry at one point, but of course we're not experts. At least personally, I know my assumption was that somehow the OH on the end could have somehow reacted with the UV light and maybe degraded the rest of the chains, or maybe somehow affected the sulfur bond, making it less polar or affecting the polarity in some sense, or using up electrons or something like that. It could have been a lot of different things. We don't know. That's one of the things that we would have to do a lot of future testing to figure out.
Well, that's actually a really good answer. I was thinking the sulfur was coming off, but yeah, it might actually make more sense if the OH just binded with something else, making it less.
Yeah, I mean, it's just because the molecules are almost identical. Sorry for not clarifying earlier. MUO and DCT are essentially the same molecule. One is just polar on the end and the other isn't. So that's why we use these two, because they're very similar.
You could easily test that with doing IR or FTIR on the surface and see if the OH is there, or if maybe like, I don't know, carboxylic acid maybe?
Yeah, maybe.
CO2?
A lot of different stuff to do. A lot of future testing is needed.
Thank you.
So we are about halfway through, so now would be a good time, I think, for everyone to have a little stretch break. So we will reconvene in about 15 minutes. So get up, stretch your legs, use the restrooms, which are located down the hall that way, and we'll be back. Yeah. So that's what I'm gonna chat with Kevin about to see if, how early those, because usually they try to set everything up at least 20 or so minutes early. So then we should be okay. Otherwise, maybe we can ask each instructor to come up and give some formal remarks. Whatever will stretch the time out. I might actually have to guys do that. Yeah. Just give you guys some parting words.
But I think you all did fine. I think it's just the feeling that you're trying to get over.
I take the speaker off?
You want to take it off?
I mean, I would like to.
Do you think we should be up here right now, or do you think we should wait?
I don't know.
Sounds gonna be like, great question.
Oh, wait, we should.
Like, no. Great question, Justin. Justin, do you want to answer the question? I mean, it doesn't really matter. I'm just sitting right here.
All right, so if everyone is ready and refreshed from a nice break, I think we're going to move on to our next group.
Okay, well, good morning, everybody. We are the official Ferrofluid group. I'm Justin Howe.
I'm Santi.
I'm Austin Haas. I'm Kevin.
I'm Tiger.
And we did our project on stabilizing buildings using a tuned mass damper using ferrofluids.
So what is a tuned mass damper? Basically, a tuned mass damper is a device that helps cancel out the motion of an object. The biggest real-world application of this is it's put in buildings to help mitigate movement from earthquakes and swaying in the wind. We have a diagram of a mass damper, one that works well and one that doesn't. And the one that doesn't, you can see that the mass is stationary. It doesn't move, it doesn't swing, it doesn't have much motion. The one, however, that's free, as it swings in one direction, the building sways in the other, and the forces cancel each other out, and the building stabilizes faster. In the real world, these take shape in the form of giant steel balls, usually, such as this one in Taipei 101. It's a free damper, and it helps to mitigate earthquakes and wind sway. There's some shortcomings of these big balls, however, because they weigh a lot in order to be able to mitigate movement of such a large building. The ball weighs about 292 pickup trucks. And at the top of the building, that's not something you really want hanging above your head at all times. So the way that tuned mass dampers work is they use momentum. Momentum has two components, mass and velocity. With the big Taipei 101 ball, it has a very large mass but a very small velocity. It only moves about 3 centimeters, even during a magnitude 7 earthquake. So what we were wondering is if we could acquire the same results using a large velocity and a small mass using ferrofluids.
So ferrofluids are a liquid that contain iron nanocrystals. And what's so interesting about these nanocrystals is that they actually they contain magnetic properties when in presence of a magnetic field. So what this allows us to do is to control their direction and therefore use it as a dampener. And of course, what we would lose in the mass of the giant steel ball, we would gain in an increase in velocity.
So let's talk about the mechanism here. You guys still remember what we're talking about all the time? Momentum. So momentum equals mass times velocity. Well, here we use velocity. We increase velocity using solenoids. So how do solenoids work? Take a look at this. Well, when a current is going through the wires, it creates a magnetic field. Well, ferrofluids, they are fluids when no magnetic field is applied to it. But if there is one magnetic field that is applied to it, it acts like a magnet. And also, solenoids are magnets. So, you know what happens when two magnets meet each other. Let's say that the tower is leaning towards the left side. We switch on the solenoid on the right, and then, swoosh, all the ferrofluids goes that way. Well, you know, the motion, it moves with velocity, which creates momentum. Will counteract the momentum of the leaning building. And then, you know, it goes back that way because, you know, this movement. So let's turn on the one on the left side. Well, it goes again. Through this process, we will counteract the momentum created by the tower leaning on both sides. And also, we can control it. Well, that is where we place a ferrofluid stamper. Normally, the traditional ones, the gigantic steel ball, they always require space up to like 10 to 12 floors. But this one, it only requires 1, which greatly saves the space.
So in order to prove that ferrofluids have the capability of stabilizing buildings, we decided to make some calculations. So first we have to find the momentum created by the giant steel ball. So the mass of this ball is around 660,000 kilograms, or that's around 730 tons. And as for the velocity, we found some recordings of the ball swaying during a magnitude 7 earthquake, which is a pretty big earthquake and requires a lot of momentum to stabilize the building. So we're setting ourselves pretty high standards here. So we found that the velocity is around 0.03 meters every 2 seconds, which translates to 0.015 meters per second. So using our momentum formula, we multiplied the mass times the velocity and found that the momentum created is around 9,900 kilograms meters per second. So let's say hypothetically we have around 1,800 kilograms or 2 tons of ferrofluid. We're already eliminating around 99.7% of the original mass, which amounts to around 26 dump trucks. So that's a lot of weight we're losing right now. So what does that mean about the velocity? How much velocity would the ferrofluid need to reach in order to match what the steel ball, in order to match the momentum of the steel ball? 100 miles per hour? 1,000 miles per hour? No, we'd only need 12 miles per hour or 5.5 meters per second. Now that's more than half of Usain Bolt's max speed. So, and also another comparison is railguns, which use similar technology using magnets and whatnot, and they can reach velocities of around 2,400 meters per second. So this shows that ferrofluids definitely have the capability of matching the steel ball and also have the potential to be even more efficient and maybe even stabilize buildings during magnitude 10 earthquakes or something of that sort.
All right, so let's get into our actual experiment. So first we started out making ferrofluids, as you can see from the other groups. We mixed the FeCl with FeCl2 with FeCl3 with ammonium hydroxide, and we made the iron nanoparticles. We then basically mixed them out with water and ethanol, which basically made our ferrofluid, which you can see right there. We then took this ferrofluid and we put it in basically a glass test tube so we could see it moving around. So you can see we put the glass test tube with the ferrofluids inside, and then we also have these things called solenoids on the left and right. Basically what these are, it's just copper wire that we wrapped around the glass test tube. And basically we would take this, the copper wire, and we connect it to these batteries, which we had 4 Duracell batteries taped together, because that's what we had. And the ferrofluid would go from side to side near the solenoids when we turned them on and away, since when we turned on the solenoids, it created an electromagnetic field, which would attract the magnetic ferrofluid. So we actually have a video of that. So you guys can see.
Yeah, all right. So as you can see to our right, the video of the results of our experiment. As you can see, when the solenoid is turned on, the fluid tends to kind of group up near where the solenoid is, demonstrating that we can control the fluid. Here we have another video where instead of using the solenoids, we used more powerful cube magnets. This kind of shows that if we have a more powerful magnet, you can control the ferrofluids even more strongly than we can do ourselves. So these results, what they mean for us is really that we demonstrate that we can move the fluids at what we estimated to be a speed of about 0.125 meters per second or 0.3 miles per hour. This is important because now we know that we can for sure generate some momentum using our ferrofluid. The ferrofluid has a mass, and we just demonstrated that we can give it a velocity. And if you remember the momentum equation, P equals mv, you would know that we now have a guaranteed momentum. This means that we can in fact use this ferrofluid to stabilize buildings, because if you can put momentum into the ferrofluid, you can use that momentum to counteract the momentum of any swaying building. And we have done all this in maybe 12 or less hours of work. So if you imagine giving us a larger time frame, how much more we could do.
So yeah, as we were talking about, if we had more time, we could definitely do a lot more, and also if we had a lot more funding as well. So you see, our solenoids, it's literally just copper wire wrapped around a test tube. If we actually had an industrial level electromagnet, it would be much more powerful, obviously, and it would do a lot more work in creating an electromagnetic field and actually pulling more ferrofluids faster from side to side, as well as a battery. We had 4 Duracell batteries taped together. Obviously, if we had a real one in a building, we'd have a much more powerful industrial quality power supply, which would obviously, again, make it much more stronger, make a lot more fluid move faster, and ultimately make a much better product.
So basically, with a super bootleg setup, we managed to actually get results in moving a fluid and measuring its velocity. So if we can do that in just 6 hours of prep and 6 hours of experimentation, if we had days, even a couple months, we could definitely get that up to 5 miles per hour. We're at 5% of our goal of what we need to just match. And since we have railguns, which use basically the same technology in a slightly different way, railguns go very, very, very fast. And that would make ours, that could very well exceed the standard that we set with the magnitude 7 earthquake in the steel ball.
Then let's talk about the future of this project. Well, as you can see, these are the world's 10 tallest buildings, and all of them have a damper in it, which means that we've got market, very large market. And, the land that are usable these days, they aren't sufficient, which means that the buildings must be higher and higher. So, yeah, we've got market. Anyway, I wonder whether you've seen an advantage of using these, because when you are using a traditional gigantic steel ball, you can just place it in the center of the building, and it barely moves. But using ferrofluid, it can be as long as the diameter of the whole building, maybe 50 meters or 60 meters. Well, that is highly efficient. Also, I would like to mention the computer program, because like we're using computer program to calculate how much voltage should be applied to each solenoid, and which solenoid should be activated and which are not. So with this, we can precisely control and we can precisely counteract the momentum of the leaning building, which means that it's more stable. And I think that's it for our presentation. Thank you all.
In your calculations, did you include the magnetic field that you need, how much magnetic field you would need to control such a large ferrofluid area?
No, that was not taken into account. But of course, it could be calculated. We just didn't do it. Sorry.
And also it adds to the weight, right? If you have a magnet, that magnet weight you have to add to the weight of the.
Could you repeat the question?
Yes, when you're computing the momentum, there is mass and velocity. Okay? To the mass, if you have a magnet, there is a mass of the magnet, right? The weight of the magnet. You need to include that as well, okay?
Yeah, definitely.
I wouldn't think so, but because the magnet itself isn't really moving, it's just controlling the ferrofluids. So the ferrofluids.
The magnet is not moving, but in your computation of showing that you have a 26 times less weight or whatever the number you show, then when you are placing it, then you need to have a magnet. You have to create a magnetic field. However way you create the magnetic field, there is a weight associated with that. Not for the computation of the momentum.
So it would be heavier. I definitely think it would add weight. But as you can see, I mean, we were cutting off 99.7% of the weight. So even if we did add it up, it would still be tremendously have less weight than what the normal steel dampener had. Yeah, if you want.
Also, adding on to that is worth noting that with the 730-ton steel ball, that's just the weight of the ball. There's also mechanisms that are used to actuate. There's pistons and controls for that, which we didn't take into account for the weight of steel ball. So there's extra mass on both sides, really, but we're just comparing the mass of the actual components that are used to affect the momentum.
And also, I would like to talk about some statistics. Normally, the weight of a skyscraper that above 600 meters, it weighs about 1 million tons. Well, compared to that, 2 tons of ferrofluids, well, you can just forget about it. But the momentum, it is very, very large.
In order to control, how do you know which side, how is it swaying before the earthquake happens or when the earthquake happens?
So the question was, how can you control, how exactly would the computers be able to control how the ferrofluid is moving within? That could just be used with like gyroscopes or whatever to sense like if the building is tilting one way, and then that can start the mechanism to calculate how much ferrofluid to move in what direction in order to counteract that movement, which is more of an engineering problem. We were mostly focusing on a proof of concept.
In your experimental approach, one of the hardest things that struck me is how do you estimate the speed of the fluid inside the test tube?
So the question was, how exactly do we measure the speed? Truth be told, fluid dynamics are kind of hard, so we kind of eyeballed it and we gave it a pretty rough estimate, but it wouldn't be like much less or much more than that, than the number that we use in our calculation. So it's relatively accurate, but of course it's not perfect because fluid dynamics are hard.
Can you explain a little bit more about how you measured it? I know that you had a video before of the ruler there. Can you explain that process?
So the question was how exactly calculate the velocity. So basically, we measured the point from basically where the fluid was bunching up when the solenoid was activated. And then we calculated the time from when the solenoid was activated to when it was all more or less settled. We used that time, and the velocity we used was about half the test tube. That was the distance that we used, because that's, again, a pretty rough estimate for about how much, on average, distance the fluid covered. So the question was about how exactly the mechanism would work in like a real world application. So what we sort of visualized was a sort of pipe system where there's pipes going in all sorts of directions, so you can exactly pinpoint what direction, or not exactly, but have a pretty controlled direction of which way you want the force to go. And also, the way that railguns work is there's a long series of magnets that are activated and deactivated in order to force an object out at an extreme velocity, which is what computers would be able to do in our system.
And please.
Would that be like a network of tubes, or would that be separate tubes on different floors?
The question is, would like to be a series of tubes or just one tube on the same floor? Well, I would like to say that if necessary, we will like put like different tubes on different floors. But actually, I think one rotator will be enough. It can rotate in different directions, and computer program, they can be precise. They can be like turn in east for 0.00001 degree, and it will perfectly match the momentum we need to counteract.
Does the altitude make a difference in the ferrofluid nature in the way it works?
The question was, would the altitude of being up in a tall building affect how the ferrofluid works? And I assume yes, but then again, we're not exactly sure, but it definitely could, it definitely could not. This is mostly a proof of concept to show it can be done, and there's more work to be done in this area.
I'm just curious, that's all. Maybe the instructors have an answer to that.
Most likely it wouldn't. Depending on the liquids, you could always have it sealed in a system, so if it has a high vapor pressure, it wouldn't matter. They would actually probably be using oil with a high density, so it would be fine, especially since most of these buildings are still designed for humans, so as long as the humans are safe, anything at that height should also.
And another thing is that NASA uses it in space, so they use the ferrofluids as in jet fuel so that they can control where the jet fuel goes in zero gravity. And so if they can get it to work, I'm sure that you guys can get it to work at different altitudes.
So next, yep, they're coming up. Good. Excuse me.
Hi everyone. Our presentation today is on water filtration and sunscreen pollution. My name is Chloe Shannon.
I'm Jessica.
I'm Ryan.
I'm Josie.
And my name is Arnav.
So what is sunscreen pollution? Every time you go to the beach, you apply suntan lotion onto your skin. Well, that same suntan lotion also dissolves into the water and can actually affect the community within the ocean. And very little research has actually been done on this field. Most of it focuses on creating a new eco-friendly sunscreen or limiting tourists to go to a certain part of the beach where they can't harm the sea life. And anyways, today we will be investigating the removal of undesirable chemicals from seawater, and we will be specifically focusing on zinc oxide, which is a key component of sunscreen. So zinc oxide is a nanoparticle that is used in sunscreen, and it works by absorbing UV light, and it protects our skin from harmful UV rays. So although it seems that zinc oxide is actually healthy and protects our skin, it is actually harmful towards coral reefs and animals within the ocean. However, if we focus on how to remove zinc oxide from the water, we might have a solution to this problem and can actually help the ocean. So as you can see in this picture, this image shows a once healthy coral and the after effects of what happened after it has been exposed to sunscreen. Basically what sunscreen does is that it bleaches the coral and it prevents it from being able to provide shelter and nutrients to the animals that live there. And just beyond just coral, all marine life is affected by zinc oxide nanoparticles, and marine life is essential to attracting tourists, and without those animals in the ocean, the economy could be impacted. And some locations have already banned the use of certain chemicals in sunscreen, such as Hawaii, but studies on zinc oxide show that it can too harm sea life.
Okay, so our question is, what is the most effective method of filtration that can separate zinc oxide from the ocean water? So we predict that zeolite A in conjunction with the membrane filter will be the most effective way to separate zinc oxide from the ocean water, because zinc oxide is slightly positive and it is small enough to interact with zeolite and its pores. So zeolite A is a crystalline aluminosilicate nano network that has nanoscaled pores that are slightly negative, so it attracts positive ions, and since zinc oxide is slightly positive, it gets attracted to the zeolite A and interacts with the pores. And then afterwards, we would use a membrane filter, which would filter out zeolite A, which has the zinc oxide attached to it.
Okay, so we broke our experiment down into two parts. The first part of the experiment was we wanted to see if we could even calculate the concentration of zinc oxide in ocean water. And the way that we did this is we prepared lots of vials, some with DI water, which is our pure baseline, and some with ocean water from Santa Monica. We prepared lots of these vials, and the next step we did is we wanted to put measured volumes of sunscreen in each vial, but we had to dissolve the sunscreen first because it was too thick to actually get a good measurement. So we dissolved it in ethanol, and then we added the drops of sunscreen to respective solutions. First, we started out with the 1 through 15 drop, but we realized the absorbance spectrum is too big of a range for this, and we stuck with 0 to 2 drops with increments of 0.2. The last step we did for the calibration curve is we measured the absorbity using a UV spectrophotometer. And the idea behind this is if zinc oxide soaks up or absorbs UV light, then the more zinc oxide in a solution, the more absorption it should have. So this is our data for the pure DI absorption, and it looks pretty similar for ocean, so I just put this graph on. And you can see here that there is a higher amount of absorption around this area, so our max absorption wavelength is 327 nanometers. The next thing you may notice is that the higher concentrations always have a higher absorbance. And if we take the relationship between the concentration and absorption, we get our calibration curves. And our calibration curves are the instruments that allow us to measure the concentration of zinc oxide in ocean water.
Okay, so once we have our water mixed with our zinc oxide, what we did next was we added 1/8 teaspoon of zeolite A. And as shown in this picture here, we filled up in a syringe, filled up with the water. And we got a membrane filter, which we put into another vial so we can see the purified water. So we can see how much did the membrane filter get out of the water.
Okay. And some people may be thinking, so you can filter zinc oxide out of water, possibly. What about the zeolite? Is that going to harm the sea life or anything? So we took scanning electron microscopes. The first one's actually found online, but the second one is a picture from ocean water that has been filtered with a membrane filter and mixed with zeolites. And the zeolite picture is on a scale of 2 micrometers, and the ocean water is on a scale of 10 micrometers. So you can obviously see that there's nothing that resembles the zeolite picture in the ocean water picture, so it's safe to assume that there is no zeolite left over.
So in this graph here, we're comparing the absorption of filtered DI water to the absorption of unfiltered DI water. So we see that, hold on one sec. So we see that the absorbance of the filtered DI water is significantly less than the absorbance of the unfiltered DI water. So that means there's a decrease after filtration in the absorption of zinc oxide. This also corresponds to a decrease in the concentration of zinc oxide after filtration since, as mentioned previously, concentration is directly proportional to how much UV light the water will absorb. Okay, so ocean water, we see a similar trend where after filtration, the absorption of zinc oxide is significantly less than the absorption of the unfiltered ocean water.
So once we finished our experiment, we figured out that the absorption of the UV rays from the water decreases once we put the membrane filter and the Z-Light A. And when we were right when we said that we can get rid of the zinc oxide, as shown in our scanning electron microscope pictures. But since zinc oxide is so small, we don't know if we just took out like zinc oxide by itself or it came with other particles. And if we had like pure zinc oxide, we would have more accurate results compared to the ones we have.
Okay, so this is a graph made based off of water that is straight from the ocean. And this graph shows the maximum absorption of zinc oxide in ocean water. So in the red box, you can see it is really low, and it's essentially nothing. But this just means that the zinc oxide in the ocean is really difficult to detect with our current instrument, which is the UV vis. And because it is not sensitive enough to detect something that is that has a concentration this small. So although it's really dilute, it is still proven to be a really big problem, and we should still find a way to filter out zinc oxide from the ocean.
Okay, so some directions we can take for the future is, as Jessica mentioned, we can increase our sensitivity to smaller quantities of zinc oxide. So the ocean is a very vast, has a lot of volume of water. So the concentration of zinc oxide would most likely be in the nanomolar range or even the picomolar range. So with our UV vis spectrophotometer, the lowest quantity we could detect was 6 micromolar, which you might think, hey, that's pretty small, but the ocean has much lower concentrations. Shoot. My bad. Okay, so next thing we can do is we can increase our specificity of filtration to only zinc oxide. So as Rai mentioned earlier, we know we filtered out the sunscreen, but we're not entirely sure if we filtered out only zinc oxide or there's other molecules that could potentially affect the sea life that we're trying to help in this experiment. Last thing I want to talk about is creating a large-scale filter. So in an effort to apply our methods to the real world, we want to create something that can be used for oceans and just much more quantities of water. So what that will entail is we have, wait, hold that up. All right, thanks. So we have unfiltered water coming in at A, and then B, we would have a mixture of zeolite. C, we're approaching the membrane filter. D is the membrane filter, and then the rest is just filtered water coming through.
And with that, we conclude our presentation. We thank you for listening, and we also want to thank Shailene for helping us with our experiment.
I'm sorry, may you repeat? So we measured the absorption by using the UV spectrometer, or the UV vis. And we shot a ray of UV light through the solution, and we did it at different concentrations. And it showed, here, I'll pull up the absorption graph. It showed, at wavelength 325, you can see with, the 6 micromolar, you can see that the absorption is 0.1 or something. And then we use some math to calculate the concentration later on.
In the seawater chart, the absorbance was actually negative. Is that a calibration issue or something else?
So there's 2 explanations for that. One is that we blinked for our baseline, we blinked it with DI water, so pure water. So we're not quite sure if there were pollutions or contaminants that may have actually pushed it under 1 for absorbance, or under 0 for absorbance. And the second one is all of these error ranges fall in the error range of the actual machine. So it may have been machine error or water error. We have not looked into how it would affect the salinity of the ocean water because we don't know how it would affect the salt water. We mostly use this experiment to focus on how we can work with zinc oxide instead of salinity. Okay, so our question was how we would do the application, and that was mentioned on our future directions slide. We would build these into like boats or something, and people could go around adding a little bit of zeolite on large scale basis. We have not given much thought to this, but that is our rough idea.
So I imagine that you were probably not able to measure the size of the actual zinc oxide particles in the sunscreen that you guys were using.
No, we were not.
Could you comment on how you could get the size of those particles and how you think the size of the particle would affect your system?
The only idea for her question was how we could figure out the size of the zinc oxide particles and how that would affect the system. My only idea about how we could measure the zinc oxide is using scanning electron microscope or something with a scale, and then we could just figure that out. And how it would affect is it would probably work with the zeolite and membrane filter, because if the zinc oxide is too big for the zeolite, it will not filter correctly. Anyone have any other ideas of how that would work?
That's a pretty good explanation. I like that.
Do you know if there are any other types of zeolites or any other material that does have a larger pore size that could accommodate?
We did not look into different materials. We were going with what we've used in the previous week. So we did not look into previous materials, but that could be a future direction.
I don't really know chemistry that well, but I was thinking, is there a way that you can just bind the zinc oxide and make it harmless instead of extracting it out?
We have not actually, her question was if there is a way to bind the zinc oxide and make it harmless. We have not looked into that just yet. That is a good idea and possibly a future direction.
Not sure if there's an answer. How do you, so a lot of these particles, you generally regenerate them so you can reuse your zeolite. I know how it works with water, but how does it work with a charged ion?
I actually,
Or can it be reused?
I'm not quite sure. We did not actually reuse any of the zinc or the zeolite filter. That would actually be a really interesting way to do an experiment. Anything else? Okay. Well, thank you.
The clicker should be, yeah.
So we did our project on encapsulating enzymes to accurately detect different concentrations of hydrogen peroxide. My name's Philip. This is Joanne, Shlok, Savannah, and Stuti.
So before we get into the details of our experiment, I want to briefly give you guys some context on what a biosensor is, because that is the mechanism we use to conduct our experiment. A biosensor is a device that uses a biological organism, such as bacteria, or a biological compound, such as enzymes or antibodies, to detect the presence and or the concentration of a substance in a solution. Usually the way biosensors work is a colorimetric scale, which means that if you have a lot of a certain substance in a solution, you get a very bright, intense color, like the bright pink you can see to the left. And if you have very little of a substance in a solution, you'll get a very light color, like the one on the right. And how are biosensors able to detect the concentration and portray these colors? It's a three-step process starting with the signal. And the signal is basically the substance that you are trying to measure the concentration of. Once you have the signal, it goes through transduction steps, which is basically what you need to get from the signal to the response. And the response is the final indicator that you use to see how much of the original substance you had. For our experiment, our signal is H2O2, or hydrogen peroxide. And the transduction steps are when H2O2 reacts with amplex red, another substance, and this reaction is catalyzed by an enzyme called horseradish peroxidase, or HRP. And after the signal and transduction step are complete, we are left with resirufin, which is a substance that colors our solutions pink based on how much of H2O2 was originally present. So what are some applications of biosensors? Currently, one of the biggest applications is for diabetics who need to monitor their glucose levels constantly. And biosensors provide a relatively inexpensive, non-invasive, and efficient way to monitor glucose levels. On top of that, the food industry is using biosensors a lot to detect pesticides and other contaminants before consumption. Another very interesting application for biosensors is for disease detection and disease screening. This is a picture of cancer because certain tumors are known to release biomolecules that are hallmarks of cancer, certain proteins, certain hormones. And you can use biosensors to detect the presence of these biomolecules in the blood, and then you can see if a patient has cancer and what the development of their tumor is like. And finally, I want to briefly talk about biosensors and their application in the environment. A lot of scientists and a lot of researchers are working on how we can use biosensors to detect certain pollutants and contaminants in the air. So there's a lot of other biosensor applications that I'm not going to talk about, but suffice to say it's a very interesting field with a lot of applications and a lot of promise.
All right, so first we need to answer the question, why is encapsulation useful? Most of the enzymes that are used in biosensors can unfold and denature in highly acidic or highly basic environments. This renders them useless, so they cannot give off a response. So we solve this by using a method called encapsulation. An absorbent gel or bead is placed into an enzyme solution. Once it has absorbed the enzymes are protected inside the nanostructures, and this prevents the denaturation of the enzyme.
This leads us to our research question, which is what method of encapsulation best detects different concentrations of hydrogen peroxide? The significance of our research is based on the applications and impact of hydrogen peroxide. One of many applications of hydrogen peroxide is a pharmaceutical application, such as cleaning scrapes and wounds. Another application is food use, such as washing fresh produce. And dentistry is also a form of application, the clinical application. Hydrogen peroxide may also be used as an antibacterial agent, such as being an additive in milk. Because of hydrogen peroxide's importance in the food and beverage industry, government officials raise the demands for stricter detection protocols. This is why our research is so important. So we hypothesized that in our experiment, we would find that encapsulating the enzyme in agarose gel would provide the best distinction between different concentrations of hydrogen peroxide. We decided to use agarose gel because we learned that through research that in similar studies, agarose gel was commonly used.
So I'm going to go over the experiment that we did to test our hypothesis. So this is just a brief overview, but in step 1, we create the assay solution or the working solution. In step 2, we're going to create the different beads and gels that will be used to soak up the solution that we made in the prior step. In step 3, we're going to make different concentrations of hydrogen peroxide to test the limits of detection. And lastly, we're going to test everything. So in more detail, for step 1, we're going to create the assay solution by putting 15 drops of HRP solution or horseradish peroxidase. We're going to use 10 milliliters of a buffer to keep the enzyme from heating too low of a pH or too high of a pH, which will essentially protect the enzyme. And then we're going to put 3 drops of amplex red. In step 2, we're going to prepare the beads and gels that I mentioned earlier. We're going to use polyacrylamide beads, agar gel, iodocarrageenan gel, and agarose gel. And with these, we're going to place the beads and gels in the assay solution for 10 minutes to let them soak up the solution. In step 3, we're going to prepare the different hydrogen peroxide dilutions with the following concentrations. We used 0.0006%, 0.03%, 0.21%, 0.3%, and 0.6%. So as you can see, 0.21% is bolded because this is the amount of hydrogen peroxide that we typically consume in our foods. And from here, we decided to go up and down. We went down to see the limits of detection, and we also wanted to get a gradient of different shades of pink that the Amplex Red will provide. And in step 4, we're going to add 1 milliliter of each hydrogen peroxide diluted solution to the wells in columns 1 through 6, as shown to the picture on the right. And then we'll add the gels and beads to the respective wells, rows A through E.
So the well plate demonstrates our final results. Each row contains different encapsulation methods, and each column contains different concentrations of hydrogen peroxide. The polyacrylamide beads in the first row and iota carrageenan in the third row only detected the presence of hydrogen peroxide, but did not pick up the differences between concentrations. Agar in the second row was unable to detect the 0.3% and 0.6% hydrogen peroxide concentrations. And agarose in the fourth row not only detected the presence of hydrogen peroxide, but it has darker pink shades as concentration decreased. Lastly, free enzyme solution detected hydrogen peroxide, but the pink shades did not vary in a pattern as the concentrations vary, suggesting that it's not sensitive to the changes in the concentration of hydrogen peroxide. In conclusion, we conclude that the agarose gel was the best way to, was most successful at detecting hydrogen peroxide because each concentration is colored and can also accurately picture the differences between concentrations as seen by the clear gradient.
So something really unexpected and really interesting to us that we saw with their conclusions is if you remember back to the first slide when I was explaining how biosensors work, we said that usually if you have more of a substance, you get a brighter, more intense color. And usually if you have less of a substance in a solution, you'll get a lighter, more pale color. And for us, we had the concentration of H2O2 increased as you move from left to right. So you would expect that the shades of pink would get darker as you move from left to right, but instead they got lighter. And the first time we thought it was just a mistake, so we redid our assay, but this is what we got after several trials. And so we're not exactly sure why this happened. Given some more time, we would like to explore this. But one possible idea that we had was that H2O2 is a slightly acidic substance, so maybe it denatured the enzyme, and that's what caused these unexpected results. Talking about unexpected results, I want to briefly go over sources of error. One thing that contributed to some error in our results might be because we were working with some very sensitive materials. I mentioned Amplex Red in the beginning, which is what reacts with H2O2 to start off the signal. And Amplex Red is very sensitive to light. It begins to break down when it's exposed to light. And so it was very difficult for us to manage and try to make sure that Amplex Red was never exposed to light when we were creating our multiple solutions and filling our gels for the assay. On top of that, to some extent, we did have some imprecise measurement. Because we were using gels, we couldn't use a more sophisticated equipment like a spectrophotometer, and we had to eyeball how pink things looked to us. And so this, of course, led to some error in our final results. And lastly, contamination. Like I mentioned, we were dealing with a lot of different solutions, and certain materials are very sensitive, like Amplex Red. And so we tried our best to make sure that nothing was exposed to light, and we were trying to keep everything safe and protected, like you see in that cup, which is completely covered. But that's not always possible, and we acknowledge that that might have factored into our final results. And lastly, for some future directions, in the short term, one of the biggest things we want to do is explore those unexpected results we got, why it got lighter instead of darker as we increased H2O2 concentration. On top of that, we want to test the same solutions in gels with various contaminants. As Savannah mentioned, H2O2 is present in food and in milk, and along with these substances come certain natural contaminants like pesticides. And so this yellow substance over here is a substance we want to use to model contaminants that we might see in food, and we can see how the different gels change their effectiveness based on contaminants. And we also want to test with different ions. So the picture on the right is copper and water, because oftentimes you find copper ions and calcium ions in water. And so testing with these materials and seeing how this changes our gel's effectiveness could also be a next step for us. And in the long term, we want to engineer gels to encapsulate specific enzymes. We were working with horseradish peroxidase, but other people doing other experiments will be working with other enzymes. And so we can try to make gels that are specific and can create the most effective environment for different experiments. So thank you so much for listening to us. Do you guys have any questions?
You mentioned that the concept of encapsulation would be helpful if you're going to be trying to test in, from peroxide in highly acidic or highly basic environments. I wonder if you have any ideas about where the use of hydrogen peroxide might encounter some situations where this would be particularly beneficial.
Well, hydrogen peroxide is a slightly acidic solution by itself, but no. In certain drinks where it might be used for antibacterial uses, they might be very acidic, so biosensors have to be encapsulated for that.
I think adding on to that, in the lab we were trying to be as sterile as possible, but when someone might be using this in their own home, the conditions might not be that perfect or ideal, and so testing with encapsulation just makes it more effective and more accurate overall.
Hydrogen peroxide is an additive in milk, but I believe it would be used more like the food and beverage industry than like the actual people. So.
Does that answer your question?
That's not my question. Like, yeah, the presence of hydrogen peroxide, you mentioned contaminant, or some other material, some other liquid or something else. So then, how sensitive your biosensor would be in measuring the concentration?
I think if we go back to that, if you guys remember that one slide that Philip talked about, yeah, right here. So the average amount of H2O2 we're exposed to is 0.21%, which is already not a lot. And our sensor can detect down to 0.0006%, which is significantly less. So our sensor is really sensitive, and it can pick up on even the smallest concentrations of H2O2.
Well, by definition, the polyacrylamide encapsulated the enzyme the best, but since it encapsulated so much enzyme, it wasn't very sensitive to the different changes in concentration. So I think agarose gel was the average, the fine line between too much and too little.
So for like retail products, like a pregnancy test, you just want to change in the plus and the minus. It's kind of a step function. For a lot of more detailed things, for instance, like a glucose sensor, you don't want to rely on color necessarily to determine the color also is really nice. We use our eyes a lot. So are there any other mechanisms in your reaction, such as electricity or some other chemical product, that you can then quantitatively send to a computer or use that as a basis?
So in our future directions we wanted to couple gel with an instrument to give quantitative results. Unfortunately, we don't have that kind of technology right now, and with the time frame we were given, we didn't really have enough time to do that.
What would the mechanism be? Is it like when the color changes, does the pH change with it? Or?
We were thinking of maybe using a modified version of a spectrophotometer.
Okay. So basically substitute the human eye with a machine.
Yes.
So you mentioned detecting H2O2 for toxicity reasons. Do you know at what level it's considered toxic?
Well, the level that we had in our slide, which is 0.21%, it's not very toxic to normal to adults, but to children and people with certain conditions, it can be more toxic.
Thank you.
All right. Also, I saw that people were feeling maybe a little sleepy because we've all been sitting for a while. So maybe just for a small break, everyone stand up for 15 seconds. Give yourself a nice stretch.
Feel free to admire this comedy gold up here.
Yes. Here, I'll...
There we go. I think it's good.
Yes. You can enjoy the spectacular comic.
Yeah, try it. She's putting in presentation mode, so if we have any notes that we have. What?
Not gonna work on here.
Pointer, I might use a little bit. Where's the pen, right? Yeah. I'll just hold it here and you can...
Does it click the slides too?
Yep.
Yeah.
All right.
All right, everybody had a good 15-second break. Nice. So, I hope you've all been enjoying the presentations thus far. Now it's our turn. So, our presentation was on creating hydrophobic coatings with eco-friendly materials. My name is Akash.
My name's Darren. I'm Raphael.
I'm Grace.
I'm Emily.
So, to start off, we first need to understand what hydrophobicity is. Now, the other group that did hydrophobicity and hydrophilicity covered a little bit of this. This is just like a little bit more detailed diagram explaining this concept. Sorry. For right now, we're going to focus on mainly the hydrophobic and the super hydrophobic parts. When we measure contact angle, we take the angle at which the solid, liquid, and the vapor in the air meet. And when we measure that angle, it's the surface and then the vapor angle. Surface and the liquid angle. So at that angle, we call that the contact angle, and that can be used to determine hydrophobicity, hydrophilicity, superhydrophobicity, or superhydrophilicity, as you can see above. We don't need to really worry about superhydrophilic or hydrophilic right now. We just want to focus on the superhydrophobic and hydrophobic because that's what we're mainly going to be covering in this presentation. Now, overall applications of hydrophobicity. They're essential for water equipment if you go swimming, on flippers, stuff like that. And scientists are always, even people, we're always looking for cheap, efficient sources for super hydrophobic coatings for our everyday items like our phones, phone cases, all the stuff like that. Current research shows that, so the eco-friendly molecule we're using is called a it's in the broad category of something called a phospholipid. So current research shows that phospholipids right now are only being used to make super hydrophobic surfaces super hydrophilic. What we want to do is turn that around. And current coatings can be toxic, like naphtha. And you'll hear from Grace when she introduces Never Wet, a product we use a lot here for many fun activities. Many of the chemicals in Never Wet can be very toxic for people. And other super hydrophobic coatings can be very expensive to make. For example, carbon nanotubes, very expensive to synthesize. So, our experiment involved a two-step process. Now, you'll see in these beautifully made images by me and Grace. Over here, we use copper metal, and we have tiles of it. So, we first start off by sanding the copper metal to get micro-rough surfaces, as you see on the screen. So, you can see those are the... Okay, thanks, Mike, for blocking my path. Those are the small micro-rough surfaces. And then we soak it. Step one is soaking it in a silver nitrate solution to deposit silver metal nanoparticles on the surface so that we increase surface area, and that way we get a nano-rough surface. After that, step two, we have our phospholipid solution. We soak it in there so that we can attach the polar part or the water-liking part of the phospholipid to the metal, and then the water-fearing part or the water repellent, it's called the lipid part, it faces away, so it repels any water. And so when we put the silver particles on there, more phospholipids can attach than previously just with a micro-rough surface.
So like Akash mentioned, Never Wet is one of the current products on the market, and it's pretty toxic with butane and propanol inside. And Never Wet can also give eye and skin irritation along with some possible brain and nervous system damage. So this leads us to our research question of, is there a more cost-efficient and environmentally friendly way to alter surface wetting properties? And the impact of our research is that research seeks to find an eco-friendly solution to alter surface wetting properties. And this can be applied to ships, pipes, etc. It can make the pipes and stuff more efficient and more resistant to water. And it can also replace, like, as I said before, Never Wet, and also TBT, which is used to coat ships, but then it's actually kind of toxic to the sea life. And our goals for this experiment is pretty much to use a naturally found and more cost-efficient molecule to make a surface hydrophobic.
Okay, so like Akash mentioned before, the molecule that we chose to use is called a phospholipid, and it's basically a type of fat molecule, and it makes up the plasma membrane found in all cells. And the phospholipid is made up of a polar hydrophilic head, which means that it attracts water, and a nonpolar hydrophobic tail, so it repels water. And the specific type of phospholipid that we used is called lecithin, and we got it from a supplement from soy lecithin. And the phosphate group right here in the head is the part that reacts with the metal ions. And lecithin is a very cheap material to get. We got 1,200 milligrams of it for $6. In comparison to the DCT that we used, we got a 96% purity, only 50 milligrams for $60. So, oh, sorry, milliliters. So this is we chose phospholipids because they have very similar structure to the DCT, meaning that one side, this side is the polar side and one side is nonpolar. So then the polar side can attach to the metal surface, and then the nonpolar side can stick out and repel the water. Okay. So we believe that the lecithin can turn the surface hydrophobic, and here's a zoomed in image of what it would look like. So here you have the micro rough structures from sanding the copper, and then the nano rough structures from the silver, and then we attached the phospholipids to the surface. And just to remind you again what our procedure was, first we took a copper tile and we sanded it to create microstructures and to also remove the oxidized layer on the front, on the top. And then we soaked it in silver nitrate for 90 seconds to then attach silver nanoparticles to the surface and create more surface area so that we could attach our polar and nonpolar molecules. And then we dropped water onto it and used an optical tensiometer to measure the contact angle.
And so in order to get these lipids onto the nanorough surfaces, we had to soak it in some sort of solution. And when these phospholipids are suspended in the solution, they tend to self-assemble into these things called micelles and bilayers, with the polar hydrophilic head poking out, which is not what we want for our monolayer, in which the lipid tail would be poking out. And so we dissolved it into hexane, water, and ethanol to see which one would prevent the formation of these micelles or bilayers. And we found that it dissolved the best into ethanol, and water it did not dissolve too well in and did not coat it very well. And hexane, it dissolved almost entirely.
This is the result of our first trial. And you probably can't see a big difference between the four on the left, but you can see that on the right, which is a control, sanded plus silver, it's flatter than the rest. So this is a closer up look of the contact angle of our third trial using an optical tensiometer. So the optical tensiometer gives us a more exact estimation of our contact angle. Copper plus silver was 82.1, that was our control. Copper plus silver plus DCT was 130.7, and copper plus silver plus ethanol in lecithin was 128.8. As you can see, the last two were pretty similar. This is a graph of our contact angle of different coatings on copper. This is our first trial using the optical tensiometer. So silver nitrate, which was our control, was 118.3. Silver nitrate in DCT was 120.5. Water in lecithin was 111.1, and ethanol in lecithin was 125.1. hexane plus lecithin was 118.6. So from here, we can see that ethanol in lecithin could potentially replace other coatings as a more cost-efficient and eco-friendly alternative. However, more testing is needed to ensure the accuracy of our data. And also, we think that water in lecithin did not result in a relatively high contact angle because water was not soluble in lecithin. Lecithin was not soluble in water as it was in ethanol and hexane. So this is another graph of the contact angles of different coatings on copper, but we did 4 more trials to improve the accuracy of our data. Silver nitrate averaged about 93.9, silver nitrate and DCT averaged about 128.9, and silver nitrate plus lecithin plus ethanol averaged about 122.3. Even though our silver nitrate and lecithin and ethanol came out to be lower than silver nitrate plus DCT, we still proved it to be effective because it was higher than our control, which was just silver nitrate. We think that to improve our eco-friendly coating, we could potentially increase the amount of lecithin that was dissolved in the ethanol, since we did use a relatively very small amount.
So the real big takeaway from our experiment is just proving that phospholipids and a naturally found and occurring substance can in fact replace a synthesized alcohol in making a surface hydrophobic. Phospholipids have the potential to make much more cheaper and much more readily abundant hydrophobic coatings, and as shown by our experiments, it is not at too much a cost of performance. And so with this knowledge, some future directions we could take is further optimizing our cost efficiency by replacing the type of metal we use for our nanoparticles. We use silver because that is what we were supplied in the lab and it acted as a control for us. But if we could replace it with something that's maybe not a precious metal, it could potentially decrease the cost even further. We could also do some more different types of testing with degradation in saltwater or freshwater for further application on boats. And to tie into that, more drag efficiency and testing water adhesion rates, again, thinking more towards boats, and also the toxicity and biological effects towards humans or other wildlife or the environment in general. And hopefully, if we had more time, we could have done this on our own, but perhaps these can be explored in the future. Thank you for listening. I think we will be opening the floor to questions now.
Yeah, go ahead.
I really liked your presentation. I like the diagrams and everything.
Thank you.
When you were starting your presentation, when you're doing like the scientific literature search, do you find any similar research using like a phospholipid, getting the fuel to coat it with the surfaces?
Sure. Okay. So the question was, when we were doing our literature searches, did we find any similar type of research that we're doing right now, where they use phospholipids to coat similar surfaces that we're doing? Correct? Is that the question? Okay. So when we did our research, I don't know about you guys, but when I did my research, I found the article about where they were using phospholipids to make super hydrophobic surfaces hydrophilic. So that's what we put on our presentations. That's the only thing I was able to find on the current applications. Otherwise, I couldn't find anything else about using phospholipids to make surfaces super hydrophobic. If you guys have anything to add. Okay. Yeah. Sure. So the question was, do you want to go?
Well, I think that
Let's see the question.
Oh, sorry. Yeah, the question was whether we think that like in the future we might want to look into temperature degradation, and I think definitely. I came up a lot in my research about how to prevent the formation of micelles and bilayers. That the big factors that went into it were temperature and pH. And I think that in the future, when we're looking at actually applying this practically, we should definitely look at those two factors. And
Nah, this was mainly just seeing if phospholipids really could work as a replacement, because going into this we were unsure if like the phosphate head would bind to the nanoparticles, or if like it would just completely form bilayers or micelles and it wouldn't even work at all. So it was really just more of a proof of concept and not really testing all conditions that it could be under.
Yeah, go ahead. So the question was, would it stick to any type of material, or do you need like specific material? Correct? Okay. So the whole point of having the polar, non-polar aspect of it is so that the polar phosphate head can stick to the metal, because they're both polar in their own ways, right? So the polar phosphate head sticks to the metal. This application wouldn't really work for plastics. So you'd have to develop other products to work on plastics. For example, Never Wet, it works on things like paper, plastic, everything like that. But this is what we're trying to replace on metals right now. Yeah.
So from my understanding, from my cooking background, I know that soy lecithin is usually in cooking sprays and it's used to make things non-stick. So my question about that is, that's a really easy application that we use for cooking. Could you think of a way that you could compare that process to the way that like nanoscience and nanoparticles enhances that?
So your question was, so since cooking sprays use soy lecithin, is there any way we could compare how that process works to how we use nanoparticles to do that?
Right, so you were saying that like Never Wet and nanoparticles is a two-step process.
Mhm.
And so specifically, how could you differentiate between it was the effect of soy lecithin and the effect that it was because it was nanoscience enhanced soy lecithin?
So are you wondering like how nanoscience was like applied into this?
Or how would you think of a way of saying that nanoscience was important in this specific?
So we actually tried in another experiment just soaking it in the hydrophobic coatings like DCT or lecithin with just sanding the copper, not putting the nano rough silver particles in it. And actually we found really no noticeable difference in the contact angle between just regularly sanded copper and the sanded copper in like DCT, soaked in DCT or lecithin. So it really highlighted how important the silver nanoparticle structures on the micro rough surfaces were in order to make a surface hydrophobic.
Yeah. Go ahead.
They were taken using the optical tensiometer. And then the droplet was using a micropipette, so like the droplet would be the same amount for each of them.
Any other questions? Yeah.
So one of the problems with a lot of these types of sprays like Never Wet is that eventually the coating wears out, right? So how would you think about testing your method of putting on this phospholipid to see if it can last at least as long as Never Wet, or maybe longer, or does it wear out sooner? How would you test for that?
So how would we test for that? Okay.
We kind of would just like try it on boats first, see how long it lasts compared to the other competitors in the industry.
I think also if we try like exposing it to each of like the different factors, like I was talking about temperature and pH, and we could also look at salinity and other different particles and like exposing them individually and seeing which ones have the most effect on degradation and trying to see how we can reduce that effect.
It might be kind of hard to see if it's on a boat, right? So like you could probably do some type of similar testing like you did here, but just maybe put it under like some type of consistent flow of water for a certain period of time, and then test after each, certain period. I think would be
Right, and just to add on to that, we wouldn't necessarily have to be testing on a boat itself. We could just take metal samples that the boats are made out, the hulls of boats are made out of, and just start with that. Yeah, Shirley.
Do you have any idea about how many phospholipids you have on your surface? Because in your diagram, you coat the entire surface. And how would you figure out that?
So your question was, how would we figure out the concentration of phospholipid on the surface? Well, I'd say we soak the two metal samples in the same concentration of DCT solution and the same concentration of phospholipid solution. I think they were both, what slide would that? Yeah, it was 0.001 molar. And so when we were given DCT to work with, that was originally at 0.001 molar. And then, so we just adapted our phospholipid to be 0.001 molar. And so I'd say it'd be like pretty close to that concentration because the particle size is, it's a little different, but it shouldn't play that big of a role in like how much surface area it covers. Plus we have the silver nanoparticles, so we're gonna get even more on top of that.
I have a fun one.
Sure, go ahead.
So you didn't show all your data on the different metals.
Yeah.
Are there any international or federal laws broken while doing your research?
We may or may not be international criminals. Currency may have been defaced. No, but in all seriousness, we did conduct some studies to see if as one of these guys had said, to see if silver nanoparticles played a big role. So we had to end up sanding pennies for hours. That was not a very fun process, I'll tell you that. And we tested them by soaking, but just leaving them as is, sanded copper, sanded zinc, and then soaking the sanded zinc in DCT and phospholipid solutions. And it made no real difference, so.
And so the metals, those weren't conclusive, right?
No, those were just like proof of concept then again, so.
Which metals did you end up using in total?
We just used zinc and, yeah, we used zinc, stainless steel, copper, and aluminum. Any other questions? Yeah. Time frame as in like how long they were soaked in solution? You guys want to answer?
Like as soon as the droplet was dropped onto it, we took like a picture.
So how an optical tensiometer works, just to add on to what Raphael was saying, is you have the surface and then you put it in front of the camera and then there's a little needle that drops a drop of water while you see the camera. So you can take a snapshot right there. Any other? Yes, Andy.
It's more like a comment. Since we had your kids, I just want to point out that Never Wet is not that toxic.
You guys touched the Never Wet all the time yesterday when you were doing your boat races, and none of you are dead. Not that toxic. We're not exposing them to toxic.
Yeah.
Okay, it's not like super toxic, but organic molecules are definitely a better alternative.
Yeah, and like the fumes of Never Wet can also be.
Butanol, I'd probably
We
be in at least
Wait, we never mentioned those.
5 years. Humans are very resilient creatures.
Any other mind-boggling questions? All right, thanks for listening.
Oh no.
Can you go to the... Go. No, actually down. My bad.
This one?
No, down. All the way down, I think. Yeah, there. The blue, green, red. R, bottom right.
You need his bar to make that?
No, we just put it on there.
Okay, that's what that logo is.
You didn't know that was R?
I don't use it. Why would I use it? What is it called?
Do you want me to do it? All right, hello everybody. Firstly, I would like to introduce myself and my lab mates. I'm Elif Narbay.
I'm Karthik.
I'm Lance Drew.
I'm Claudia.
And I'm Caroline.
And today we'll be talking to you all about our investigation in which we explored the most efficient organic dye color to create the most efficient solar cell.
With the urgency of renewable energy increasing, our curiosity on how we as aspiring future scientists can meet such demands has increased immensely over the course of this program, and we hope that we too can pique a little bit of your interest in the preceding 10 minutes.
So solar energy is a renewable source of energy that uses photovoltaic cells, an electrical device that converts the energy of light into electricity. Dye-sensitized solar cells, or DSSCs, are a part of the thin film solar cell group. So a lot of research is currently being done on DSSCs because they are more cost efficient, because natural dyes can be found in plants, whereas silicon is more expensive. And however, DSSCs are not as efficient because liquid electrolytes are not stable in high temperatures. Hence, quasi-solid state electrolytes are being investigated, but they don't diffuse fast enough across the solar cell with redox reaction yet.
Yeah. So how does a dye-sensitized solar cell actually work? So as we can see here, this is the structure of the solar cell that we made. So this is dyed titanium. We use titanium because titanium increases the surface area to allow for more dye binding, and the dye absorbs light. And when the sunlight goes through here, the electrons in the dye gets very excited. So it needs somewhere to go, so it goes through that loop and goes back here to the catalyst, which speeds up the reduction of the electrolyte, and the electrolyte completes the circuit.
Okay, so now I'm going to talk a bit about our research question hypothesis. So we were basically wondering how we could increase the efficiency of a dye-sensitized solar cell by changing the dye color. However, as we did this, we also wanted to keep price in mind because, as Claudia was saying, dye-sensitized solar cells are cheaper than silicon solar cells, but there are still some expensive components that are usually used for the most efficient solar cells, such as ruthenium, which is used in the dye, and platinum, which is used in the catalyst. So instead of using ruthenium, we decided to try using red cabbage juice. So that's plant-based dye, so it would be cheaper. And it also has an interesting property in that if you change the acidity of the liquid, or a liquid, and add that to the red cabbage juice dye, then that will change the color of the dye. And since we want to see which color is the most effective, we decided to use the red cabbage juice dye and change its color using acidity. Here's a graph, and we were expecting that if we had a purple dye, then that would be the most effective because, as you can see, though the sun emits various wavelengths, it has like differing intensities, and it's most intense at around yellow. And so purple is the opposite of yellow, meaning that whenever you hit purple with yellow light, then the yellow light is completely absorbed and none of it is reflected, which is why it doesn't appear yellow. Considering this experiment, we also wanted to look into the adaptability of dye-sensitized solar cells, because since we were using the cabbage juice dye, we thought maybe we could alter the color of the dye on the solar cell itself to make it more effective under different types of light, which is also important because dye-sensitized solar cells are different than other types of solar cells in that they work better than other solar cells under lower amounts of light. So that means they could also be used inside and used to recollect energy from like electric lights, as well as being used in different types of the world where there are different areas in the world where there are different types of light.
All right, so the pH level is affected by the concentration of hydrogen ions in a solution. The pH level affects the color of the anthocyanin protein in the solar cell, because the anthocyanin protein is given its color due to the conjugation, which is the alternating single and double bonds that gives it its color. And in the C ring, the first part, and the B ring, the fifth part, those two particular are are the main regions where the patterns of substitution are affected. So here you can see different chemical compositions of different pH levels, and as you can see, is at this particular part and this particular part where its element or whatever molecule is there is determined the color of each different pH level.
So our project was divided up into 2 major steps, the first being the dye solution preparation and then the solar cell assembly. We prepared the organic dyes by changing the pH levels using hydrochloric acid, ammonium hydroxide, and deionized water to dilute the cabbage juice. In total, we assembled 32 solar cells. Here is a small sample. The most critical step probably had to be the first image over there, illustrating the titanium nanoparticle coating. As once again, Lance explained, it not only does it increase the surface area and therefore the intensity of the absorption, but it also acts as a docking site for the dye. And then here are a couple more steps of the assembly of the solar cell. We had to bake the titanium-coated plates on about 250 degrees Celsius without burning the lab down, actually coat the glass plates with dye, and then assemble the solar cells together. We went outside to measure the voltage and the current produced, and we also tested its electrical output inside with LED flashlights. And we had to measure the electrical output during the same time of the day in both experimental days to ensure that the intensity of the light remained as constant as possible.
Okay, so now we're going to go over a bit of the data. I was wondering if, Claudia, could you pass the solar cells out? So first we tested under sunlight, and we had between 3 and 6 solar cells for each color, that is each pH. So we started out with 3, but then a lot of them failed, so we ended up making more. And you'll notice that we have very large error bars, so the meaningfulness of this data is actually kind of questionable, but I'm still going to analyze what this could mean. Okay, so first of all, we have a pH versus current graph. So like the red, for example, is a pH of 1.5, whereas the yellow is a pH of 12, so 1.5 would be the most acidic, and we found that the more acidic dyes worked better. Looking at the solar cells that we passed around, so we were kind of surprised that the purple didn't do better because we expected purple to be best at absorbing yellow light. However, we found that actually when we soaked the solar cells in the dyes, the ones in the red and pink dye ended up turning more purplish colored, and the purple itself ended up looking more bluish, while the more basic ones ended up looking more yellowish than maybe bluish or greenish. So that could have affected our results. And we also found that the basic dyes didn't tend to work very well. Current is charged over time, so we expected that if more energy would be put in, more electrons would be excited and more charge would flow. Whereas voltage is difference in electrical potential. So it basically describes like the amount of work necessary to move a charge from like one point to another in a circuit. So we didn't really expect that to be affected so much by the how effective it is, how the solar cell absorbed the light. So we didn't really see any trend in the voltage graph. So secondly, we tested the cells with flashlights after we tested them with sunlight, and we think this might have affected our results here. So they were fairly even in the more basic region, and surprisingly, the pH 1.5 and 3 still did better than the others. We're not quite sure why this is, because the flashlight was basically white in color, and white's basically a blend of all the colors fairly evenly. So we thought that maybe, so we tested them with sunlight first and then with flashlights afterward, and that meant some time passed. So the electrolyte may have sort of limited the electrons from flowing, because we thought it might not have been able to keep up, and it may have stopped completing the circuit as effectively, because it's supposed to be the thing that carries electrons back through the glass. And again, voltage didn't really show much of a trend and seemed fairly even. So that may have, it may have been because it wasn't really affected so much by the absorbance of each dye.
So Here's the equation used to determine the efficiency of the solar cells. The electricity produced is found by multiplying the current by the voltage, and the value for the solar energy absorbed is derived by dividing 1,300 watts per meter squared, which is the amount of power emitted by the sun in this geological region, and then multiplying that by the area of the titanium coated glass, which is 4 centimeters squared, and then dividing that by 100 meters squared to essentially get the exact amount of power that the solar cells we made could absorb from the sun in an ideal situation.
Yeah, so here is the result we got. As we can see here, this is from our experiment under sunlight, and red dye has the highest efficiency here, while the blue dye has the lowest. And this is from our experiment with flashlight. As we can see here, the pink dye has highest efficiency, and the others are generally really low.
So we used a UV vis spectrometer, which stands for ultraviolet invisible absorption spectrometry. And these are the dyes that we tested, and the one at the bottom is just water to blank it. And so first we blanked the UV vis to eliminate the water in the other dyes like showing up in our results. And so this is the water right here, and that's the cuvette with dye. And so what the UV vis does is that it shines a light onto the cuvette that contains the dye so we can see the absorbance of light. And we were able to collect the data to see within what wavelength of light will the dyes absorb more. And so these are the results, and everything below 300 nm is proteins and RNA from the cabbage, and this is why the red, pink, purple, and blue dyes started to rise again near the end. And so the red and pink dyes absorb more of light in the 500 nm range, except red has a higher absorbance amount, and that means it absorbs more green light, while the green and yellow dyes absorb more the 400 nm range, and so that means it absorbs more red and orange red light. And then the blue dyes barely absorb anything, but it absorbs mostly the orange light, which is in the 600 nm range.
So based on the data we got, we found that it was the redder dyes that were more efficient. And this was based on the fact that under the flashlight, the redder dyes was the second most energy efficient. And under the sunlight, it was the most energy efficient. So to further our experiment, we would like to have a larger experimental size so that we could actually see a trend in the dye color, the pH level, and in the actual energy efficiency. And we would like to use a machine spread spin coater to spread the titania consistently, because the role of titania is to provide a nano surface on the actual glass plate so that there's more surface area for binding with the dye. And by having it hand spread, there's a lot of variation between the different glass plates. And of course, our results were partially based on the region we're in. Due to the Tyndall scattering effect, different regions around the world will receive different colors of light as the peak of their emission spectrum. Can you see the thing? As you can see here, this is the sun, and based on the angle at which it hits the Earth and how long it actually has to travel into the atmosphere, different high energy level lights would scatter out, and different colors of light would actually reach the surface. For example, in Antarctica, it may be a green light that may enter the surface, and thus it may be a reddish dye that could actually have a greater effect on the DSSCs. And
So thank you for listening, and thank you to our mentor, Zach. Any questions?
Questions?
Thinking about the cost reduction and the idea of using something like cabbage as the basis for it, are there any alternatives to titanium dioxide as the sort of the substrate that might be used if you had infinite amounts of time to experiment to cost reduce it further?
All right, good question. So the question that he asked was, so we use the cabbage juice as as a more cost-effective, what's it called? A cost-effective dye to soak it in. And what he asked was, were there any other alternatives to using titanium, the titania dye to coat the nano surface with? And essentially, we used the nano surface. We used titanium because that was the resource we were given, and it was fairly cheap because you can find that in white paint and other types of paint. But if we experiment, if we experiment further, I'm sure we can find a better and more efficient nano surface coating. Yeah, thank you. I'm sorry, could you repeat that again? Right, so, right.
The question was, what could we possibly do to increase the efficiency? And one of the things is we're using a very small surface area for our solar cells, and once again, it's more of a proof of concept. But if we did have larger solar cells to work with, the efficiency would inevitably increase as well. Does anyone have anything to add?
Yeah, also for context, I think the highest efficiency that's been achieved for a dye-sensitized solar cell is 13%, whereas ours was less than 1%, so ours was really bad, but the highest efficiency also isn't really high.
And battery storage.
Anybody else?
I think it's really cool that you guys were able to use the same dye, but just change the color of it by just changing the acidity of the environment. Were you guys able to take like a sample made with red dye and then just added acid to, or add base to it to change the color and then measure the efficiency?
So the question is if we changed the dye, the pH levels by just adding acids and bases?
Yeah, so you have one sample, let's say it's a sample of red dye.
Mm-hmm.
Have you tried adding base to it to make it into a green dye? Like on the solar cells, what you tested?
Oh, yes. At the end, we did have some time to do that, and we didn't add the data because we didn't really have that much data, but we played around with a few solar cells, and we added acids and bases, and there was some efficiency increases with the acids and then decreases with the bases when we added acids and bases to them. But we didn't have enough time to come up with like a solid conclusion for those trials. Yeah.
Does the pH of the electric or the dye affect the solar cell in any other way besides the color? Like, does the pH have an effect on the other aspects of your solar cell?
Based on the scientific what? Oh yeah, my bad. Sorry. Yeah. So basically, what she was asking was there any other effect that pH, like adding an acid or a base, had on the cabbage dye, other than its color? And based on scientific literature we read, we found that when you add an acid or a base, it partially changes its chemical composition, like its structure, which was.
We're really throwing it back.
All right, come on.
I think what Shannon was asking is, does the acid or base affect like the electrolyte or other parts of the solar cell?
The acid and bases would affect how much energy you could get, but it wouldn't necessarily. It could, but it wouldn't. From what we found, it wouldn't necessarily affect the other parts of the solar cell.
Yeah, though if we did have time for future research, it might be interesting to try keeping the color of the dye constant and then just changing the pH to see if that changes something about the current or anything like that.
Or perhaps using different plant sources and different anthocyanins to see if pH has anything to do with it as well.
everything. I just had a couple of announcements. So, whoops. No, Okay, so first of all, we need to thank all of the students for some amazing presentations and congratulate them, because that was really lovely. I'm sure that you guys all can tell what an impressive amount of work they were all able to complete in 2 weeks. And it's really not easy to stand up in front of, a lot of people, scientists and non-scientists alike, and give a scientific presentation and answer questions. And so they all did a really great job. And students, I hope that you guys all appreciate the degree to which your presentations also greatly improved from when you started this process to actually your final presentations. Like, they were all really, really stellar, and you guys did a lot of hard work, and I hope that you guys got to see how the workshops, along with the experiments, all kind of came together for the projects. Because I know that, in a science program, we all want to say that the most important part is the science, and it is. I mean, it's great to learn about nanoscience, but it's also really important to learn about all the other skills that come with being a scientist, like devising an experiment, how to find proper information, how to present information that you've obtained. And all of those skills are really not that simple, and they really require a lot of work and a lot of practice. So I'm really glad to see that you guys all did such a good job. I also really wanted to give one more big thank you to our instructors. So let's all thank them one more time. Because they all worked extremely hard with all of the teams, acting basically as PIs for their own little mini labs to make sure that all of the experiments were going well, that everything was safe. They were giving so much feedback, and they worked really hard these last 2 weeks, and even before then, to make sure that everything was ready before the program started. So thank you guys all very much. You guys are amazing. So 2 more quick announcements. So first of all, much like our end of week 1 survey, we have another end of program survey that we would really, really love to have your guys' feedback on. So it doesn't have to be right now, but before Monday, please take some time, go to this bit.ly link, and please take some thoughtful time to fill out the survey, because we really do take your comments very seriously, and we are constantly trying to improve the program and try new things based off of your feedback. So please give us feedback. And please also give feedback on the dorms, because the dorm structure was also very different this year. And that's not something that we have as much control over, but we can also provide that feedback to summer sessions. So please give us all the feedback that you can. We'd really appreciate it. And we will also email this link to you, but I wanted to show it now just in case. So final announcement, before we go and enjoy some nice food and beverages at the reception, I would love to have everyone go outside under the CNSI logo so that we can take a group photo of everyone before y'all depart. So with that, let's all head outside. Thank you guys all so much, family, friends. Great presentations.